Welcome, everyone. My name is Veljko Prodanovic. I'm together with Milan Stojkovic. I'm coordinating this project called Artifact, or Artificial Intelligence for Flood Resilient Infrastructure. And today is the second of our training session, expert training session that is about, that is about 2D flood modeling in urban context. So we have colleagues from IHE Delft, TU Delft, and TU Haha that will be joining and giving us some great lectures today. Maybe a little bit about the project before we begin for the ones that they don't know. So the Artifact project is about using AI for flood resilience, including early warning models and early flood warnings, and using nature-based solutions for increasing the resilience, particularly in the cities. So small-scale MBS solutions. It's part of the Horizon Europe Green Deal initiative and Institute for Artificial Intelligence Research and Development from Serbia is leading the project together with partners from Delft University of Technology, TU Delft, Delft Institute for Water Education, IHE Delft, and Hamburg University of Technology, TU Haha. Within the Artifact project, other than the standard research that we'll be doing in these areas, we have also education sessions. So we have planned six expert training events like the one today over the next 3 years. So this is end of first year of the project. So this is the second training event. The first training event was in May this year, and you can find the link to the whole training event here or on the Artifact website. So it's on YouTube as well. So if you want to learn a bit more what was taught in the first expert training event, it's online and available. So this one also is recorded, as you can see, and will be available online after the event, probably a day or two after this event. So you can go back through it because we have a long program planned for today. So you can go back through it slowly if you missed some sections, and you can rewatch, or you can share it with your colleagues who couldn't make it today. Within the Artifact project, we also had 3 summer schools. First summer school was this year in July. It was in Serbia, in Novi Sad. It was an amazing event. There were more than 20 young researchers who attended. We had 4 days of great workshops and lectures. We had a hackathon for our early stage researchers, and we also have a visit to the trilateral company that does gaming software for Epic Games. So it was very interesting, but maybe even better next year. We're already starting to advertise our next summer school in Delft, Netherlands. The registrations are open as of today, so hot off the presses. You can register via the website. There's a link for registration. There's a limited spots available, so please register on time. And there's a detailed program is on the website as well. I don't want to talk too much about it, but it's in July next year in Delft. So it's going to be co-hosted by IHE and TU Delft, and it's going to be very fun. So please join. Looking forward to seeing a lot of you in person next year. So for today, as I said, we have a full program of lectures. the program will be hosted by Professor Zoran Kapelan, who I'll turn to in a minute, from TU Delft, and most of the lectures, well, actually all of the lectures, unfortunately, we had apologies from Dr. Natasha Manojlovic for today. She won't be able to attend today's lectures, so all of the lectures will be delivered by Professor Zoran Vojinovic, and we'll get the slides from Dr. Natasha, and we'll upload the slides together with this presentation. But so we'll have Zoran Kapelan moderate in a second. We'll make a few short breaks in between as well, so you can grab some water and refresh a bit, and we'll have a longer break for lunch. So these Q&A sessions, I want to point out to them, these are very important to us, so please don't be afraid to ask questions. There are no silly questions. There are only silly answers, but I'm sure Vojinovic will do great answering questions, so there will be no silly answers either. But please don't be afraid. I know there's a lot of young researchers among us today. Please ask whatever you think is relevant, or maybe it's not relevant, but you're just interested to ask either Zoran or Zoran Vojinovic or Kapelan or ourselves. So please engage with us. It would be great to hear your voices. So we have 72 registrants for today's event from very diverse countries across Europe and Asia, and most of them are from academia or research, but we have quite a few people working in business sectors, in industry sector. So we have a nice diverse crowd today. And yeah, a lot of you want to learn more about floods and AI and modeling. So without further ado, I want to pass it on to Zoran Kapelan, a moderator for today's session, to introduce Zoran Vojinovic, who will be your teacher today. Zoran, please.
Thank you, Veljko. Hello, everyone. Welcome to the second expert training. Before I introduce Zoran, I just want to echo what Veljko has said. After Zoran's lectures, we'll have a Q&A session. This is a training event, so feel free to ask anything. Don't worry about is it right or wrong, question of this or that. Okay, so the topic of today's training is 2D flood modeling. And we are lucky to have Zoran Vojinovic with us, who is a well-known expert on this topic, has been working on this topic for a number of years, has led large European research projects on these topics, on flooding in general and nature-based solutions. So without further ado, Zoran, please start the lecture.
Thank you, Zoran and Veljko. It's my pleasure to give some lectures today on this very interesting topic of 2D flood modeling. The plan for today is that we are going to have a session until 11:30, and then there is a Q&A from 11:30, well, speaking of the Central Eastern European time. And then after that, we're going to have another block of an hour and a half from 12:30 till 2 o'clock, followed by the Q&A again for about 30 minutes. In the first block, which at the moment states that it will be data collection and processing for 2D flood modeling, I will first speak about the general principles about flood management and why do we need models, just to set the scene. And then after that, I will move into the data collection. So it might be good that we break for 5 minutes in between. So we go on with let's say 40 minutes, and then we have a 5-minute break, and then we go back for another 40 minutes, and then we finish the first block, and then we go to Q&A. The 5 minutes is really just the toilet kind of break, very short, and we're going to keep it to 5 minutes. And then later on, after the Q&A and the lunch break, there will be, as I said, another an hour and a half block, but then I would break it again into 2 blocks. with 5 minutes break in between, where in the first block I will talk about the case study of Dhaka, Bangladesh, where we have been working for many years and had a number of students going through IHE Delft, and we collected enormous amount of data. So I will, through that case study, show how 2D model can be coupled with 1D model and in use for the flood simulations and production of flood maps, flood risk maps. And after that, I will go more with other case studies. There will be one from Ayutthaya, from Thailand. Again, 1D, 2D models coupled. I will show how that was done. And given that we have more time, hopefully, then I can do maybe one more case study on. I have several options. One can be for Saint Martin, which is the island in the Caribbean. So that's the plan, and I will start sharing my screen. Okay. So I hope you can see my screen.
Yes, we can.
Okay, that's good. Maybe I need to do something on the side or not. This is okay.
Okay, just need to run it in the presentation mode. We can see the next slide as well.
That's exactly what I was thinking, if that's going to show.
Just go to display settings.
Duplicate,
yeah.
Yeah. And then becomes that, yes. Yeah, no problem.
Yeah, now it's fine.
It's a non-issue. Okay. So, as I said, first I'd like to set the scene about flood modeling in general. As it was introduced before, I do have appointments at the IHE Delft, where I'm actually based, but also I do have appointment at University of Exeter, also here at University of Belgrade, and also at the National Cheng Kung University in Taiwan, where I just came from 2 weeks ago. Yes, besides these appointments, I've been working for 25 plus years in both academia and industry, and always in the water industry. And my expertise is in planning, modeling, design of water, environmental systems, hydrometeorological risk assessment, primarily floods, but also in recent time also I did some work on droughts. Nature-based solutions. I've been working almost all my professional life on nature-based solutions, and in the last 15 so years, very much for the purpose of climate change adaptation. And my background is in hydroinformatics. What I'm going to present today is very much included in some of my publications, some of my books. I co-authored a book with Professor Mike Abbott, and that's the book with the title Flood Risk and Social Justice, and in 2023 was the 5th bestseller. In that book, you can find a lot of material that we're going to present today, and also the book on urban hydroinformatics, which I co-authored with Professor Roland Price, particularly on the data collection, processing, and also about the 2D modeling and 1D modeling, and also how to resolve these equations and things like that. So very much the books, Flood Risk and Social Justice, and the other book on urban hydroinformatics will be used here for today. Just to mention a little bit about my expertise and in connection to my expertise, the areas where I worked, very much in Europe, but also in Asia, Central and South America. I spent also some time working on different projects in Colombia and Saint Martin in the Caribbean, but in Asia quite a lot. I worked for a period of 10 years on many projects for Asian Development Bank. So besides the artifact, I've been leading projects for the European Commission on the topic of flood risk mitigation, and also about the nature-based solutions. The examples are Pearl project and Reconnect, which we just concluded this year. So the learning objectives for today's course on these lectures is to provide you with the basic knowledge concerning urban flood risk management and simulation using physically based models. So no AI, no data-driven models, so it's really physically based models based on physics. with a focus on two-dimensional models, covering the key concepts and practical applications through the case studies, and hopefully this will enable you to be more effective in applying the new knowledge and supporting tools. I'd like to also mention that unfortunately, because of the type of this lecture today, there won't be any exercises that we can involve the participants. But if you, at the end of this course today, if you develop interest to join us, perhaps in the summer school, there will be good opportunity, because then you'll be able to set to work on these kind of models and set up these models and produce simulations, and even further do things, use them in conjunction with some artificial intelligence type of models, data-driven models. So today I will be just demonstrating, and unfortunately there is no work that we can engage you all, and I hope that you will still be finding this useful. Okay, well, why do we do modeling? Why do we bother with numerical models? Well, if we are to reduce disaster risk, particularly the flood disaster risk, then we have to deal with different dimensions of disaster risk. If you go to any literature on disaster risk, you'll find that the key components or key dimensions of disaster risk are the hazards, vulnerabilities, and exposure. And typically in practice, people combine hazards, actually vulnerabilities and exposure together. And then the second dimension is hazards. So the hazards are typically obtained through numerical models. And this is why they are very important and fundamental for flood risk assessment. Whereas the vulnerability assessment is done through different kind of exercise, can be desktop exercise, can be field work. But then at the end, these two variables are overlaid to produce the disaster risk maps. So that's why the models are playing a very, very important role for that. So another important thing is that when we deal with the floods, and particularly flood modeling, we choose a particular event that we want to perhaps calibrate the model, but then after that, when the model is calibrated and fit for purpose, then we proceed with running different scenarios. When we run different scenarios, we choose rainfall, which can be of a different characteristics, can be potentially 1 in 100-year event, which is a 1% probability. And then we run the simulations, we produce the flood maps, we potentially compute the impacts and damages, and then we state that this is the 1% chance that this event can take place, and this is potential amount of damages and impacts that we can incur. If we go with 1 in 10-year event, obviously that's a different probability, 10% in this case, and so on. We can go with 20 years, 50 years, and this is what defines the probability of the flood risk. So since we're going to be doing the modeling, the models are, as I said, used to estimate the hazards. So hazard is a phenomenon which has a potential to harm humans. So it is a threat, not the actual event. And it is typically, for the purpose we are talking about, is a flood water resulting from an event. And what you see on the screen is the image from the Malecón in Havana, in Cuba, which often floods from the coastal system, but then also the drainage system that comes out from this urban area, from old Havana, cannot discharge directly, and then you can get a combination of the problems between the drainage systems and also with the coastal waters, and this is very tricky and complex to deal with. So moving on, I've just mentioned that the different rainfall events can be, of course, ranked in a different way. You can use variable plotting position principles to rank from a series of number of events that you can say this is my 1 in 100 year, 1 in 50, 1 in 20, and so on. And then you can use these events to run through your models. And then what you get out is, as I said before, if it is 1 in 100 year, it's a 1% probability for that particular scenario to occur. A couple of words about the vulnerabilities, because I mentioned hazards in the context of risk. So another important dimension there is a vulnerability. Vulnerability is, there are many different definitions that you can find in the literature. It can be defined as an inability to avoid potential harm. And yes, you can find there is a disaster risk community defines vulnerability in different ways. You can find, I Googled recently, you can find maybe more than 30 different definitions, but I'd like to stick with one, which is that vulnerability can be defined as inability to avoid potential harm. When we talk about vulnerabilities, and particularly in the urban context, which is the context of today's lecture, we need to kind of break down the components in urban area. We have physical infrastructure, objects, and that's a built environment. Then we have nature, environmental features. Then we may have some important economic centers because it's in urban area. We have institutions which function in a different way, and they have different responsibilities, particularly when it comes to dealing with hazards. Some of them are directly involved, some of them are indirectly involved. And then, of course, we have society, we have people. So all these different aspects can be vulnerable in a different way. So how do we go about that? We try to assess the potential vulnerability of the physical systems, infrastructure, roads, buildings, houses. And then on the other hand, we also look into the vulnerability of environmental systems, the nature aspects, people who are exposed, economies, and also institutions. These are some sketches to kind of illustrate what the vulnerability is. This is a guy who's trying to fix his truck. Obviously, you will say that he's vulnerable, or the likelihood that he may get injured depends on the poles that he's using to keep this truck up. So obviously, we would agree that he's vulnerable. You can come up with many examples. Other guys who are working in a particular environment, not very well protected, you will say that they are vulnerable. And you can find these kind of examples in many places. This is another example which I like to show to my students. So this is if you're dealing with some biological hazards, obviously that if you come unprotected, then you are vulnerable, unless you are, let's say, a teacher or course instructor who is observing what the students are doing, and so on and so on. So the risk represents a combination of different things. As I said, typically we break it down to at least two dimensions. It's hazards and vulnerabilities, and again, vulnerability is one side of the coin. On the other side is some people define resilience. And of course, exposure is an important thing. But again, in the practice, particularly in the flood risk management practice, people would combine vulnerability, resilience, and exposure into one and express it in a spatial map using GIS. And on the other hand, we have numerical models to tell us where the flood zones are. And then we again represent it in a GIS, and two-dimensional models are very well convenient to produce flood maps, because they are obviously in 2 dimensions, and which is much different from if you get a result from 1-dimensional model, which you need to extrapolate, and that can cause all kinds of problems. So anyhow, 2D models, great for hazard assessment, and then we combine them with vulnerabilities and other dimensions to express the risk. So just a couple of words about the floods in urban areas. If we have floods from the sewer systems, we could say that those are the pluvial floods, because they result from insufficient capacities of the drainage sewage system. If there is a river running through, and the source from the flood comes from the river, then we would say it's a fluvial flood. If we are situated in the area which has some hills, mountains, where the water rushes down, then we would call it as flash floods. Obviously, as I showed before in the example of Havana, which sits right next to the coastal waters, and if you have tropical storms and things like that there, then obviously they would face coastal floods. We may also differentiate another type, which is the groundwater, which typically responds with some delay. when you compare to the peak rainfall. Takes time for the groundwater aquifer to get saturated and to start showing up into basements, typically in urban areas. And then, of course, you can have a combinations. If you have an urban area which is situated between the coastal zone and also has a river network, river system next to it, and then maybe it could be some hills, and all of that, you may find all these combinations. Not very often, but it may happen. So I will speed up through this. This is an example of kind of flash floods from the hilly terrains, and this is a simulation of a 1D, 2D model, which I will come to it in a bit. So from the numerical models, when we aim to go into the flood hazards, we obtain water levels, velocities, durations, and maybe if we are dealing with some water quality issues, we may also run some advection dispersion processes, and then we get some concentration of pollutants. So these are the typical variables that we get from our numerical models that we need to that we can use to produce the hazards. And of course, choosing what we are going to, our choice for what we are going to use to produce our hazards will depend on the physics and the terrain, and also the type of the flood. If it is very slowly moving water, maybe sometimes from some fluvial floods, the water can propagate very slowly in time. Maybe in that case, your velocities are not that dominant, and then you may end up just using the water levels and maybe perhaps durations as your key variables to express hazards. If you're dealing with the flash floods, then obviously velocities are very important for you, and then you may combine them with the water levels and maybe not so much with the duration of these events, because these events can sometimes take just minutes or maybe an hour to dry out. And then, of course, if you are concerned with the water quality in urban areas, particularly if we have a mixture between the sewage in combined systems, then you may want to also look into the advection dispersion processes and look into the concentration of pollutants into the flood waters, and then use that. Okay, well, this is what we get from our 2D models, but I will come back to it later. I would like to now briefly touch upon some other things. I'll just jump through these presentation slides. Yes, talking about the flood modeling, we can look into the drainage system, because the focus of this lecture is on the urban areas. What can we find in urban areas? Typically, is the major and minor system, people call it. In some places around the globe, they call them primary and secondary. Whatever the case is, we will have pipe network system, which consists of pipes, can be also in combination with open channels. We can have, obviously, we'll have manholes. Also, there could be some pumping stations, overflows, things like that. And then you will also have water running across the streets. So then at some point, maybe the water, when the pipe network system surcharges, the water will pop out from the manholes and run across the streets, and maybe later the water will also be collected through the catch pits or gully pots, and then come back to the drainage network. So there is a continuous interaction between the below ground and above ground systems, and that sometimes plays important role in our understanding of the physical processes, and our models need to also take into consideration some of these interactions. So the flow domain can be one-dimensional, two-dimensional, or even three-dimensional if you want to. And of course, the coupling between these models can be in the way of coupling two one-dimensional models, or coupling one-dimensional and two-dimensional, or you can even incorporate a third-dimensional model. Obviously, there is a price to pay if you run only one-dimensional model. It can be much faster compared to the two-dimensional model, which is computationally more expensive and takes more time. Of course, it will give you much better results across the flow domain compared to the 1D model if you need to extrapolate the results but the price to pay could be a numerical simulation. And nowadays, what we try to do is to, besides using very powerful engines to compute that, which can sometimes, with the large networks represent and large model domains represent still a challenge and takes a significant amount of time, we could try to speed it up with the use of some AI models, but that's a different discussion. So, so what type of a model can be used? There are many different types: stochastic, deterministic, hydrologic, hydraulic, lumped, distributed, physically based, AI or data driven, and so on and so on. What we are going to focus here today are the deterministic models, not stochastic. Also the models which will combine hydrology and hydraulics. The models which are very much lumped, but the way how the catchments are delineated and connected, they act in a way like a distributed, but they are very much lumped. They are very much based on physics, and we'll touch upon some of these equations. They're process-based, and usually we like to run them in a full dynamic wave approximation. And there are other options, which I will mention in a few minutes. The models we're going to look today also can be set in a low resolution or high resolution. So you can have a very few computational points, or you can have so many that really gives you very high resolution results. Today, we will also look into the coupling between the sewer, surface flow, and also how the two work together. We will also look into the package called Mike Plus, which is a product by DHI. Of course, there are many other products. At IHE, we have also developed our own in-house engines, but because and there are many other researchers who develop their own tools. However, often these tools, in-house tools, they lack with a proper graphic user interface, and the commercial models are very much convenient for that purpose, because there are so many years that have been used to develop these models and bring them to the users in the easy way to set up and to run. So we will look into one of these models, and there are many more. I've chosen DHI because I personally spent almost all my professional life working closely with DHI colleagues and also using their software for their work. And we will look into 1D, 2D models. So, just a few things here. I mentioned that the objectives of modeling are to assess the flood risk, but there could be other things. You may want to design your system. You can very well use your models for that. You can use the models for emergency management. In real-time operation, you can use your models for pollution, health problems. I also mentioned that you can assess the effects from urbanization, climate change, and all these things. So models are very, very much important for now, for these days, particularly dealing with the climate change or impacts from weather extremes and things like that. Okay, so this brings me to the next block, which I will just now introduce a few things, and then we can break for 5 minutes, very, very short break. What data is needed to set up numerical models? And because I said today that we'll be working with 1D and 2D models, and 1D models are used for pipe network system or open channel or combination between the closed conduits and open channel network. So what we need geometry information of these networks. We also need information about the terrain. We need information about the rainfall. And then, of course, we need the information about the land surface in terms of that's very important for hydrology model setup, in terms of what is percentage of pervious, impervious area, what are the slopes, depending on the hydrology and what we are setting up. So we'll have hydrological data, we'll have geometry data, we'll have also some time series data, in a sense of because when we set up the models, we always need to calibrate the models, because the model which is not calibrated is potentially useless, and we don't want to run useless models when we assess the flood risk, and particularly if we want to make some decisions to improve the system, we want to use reliable models, and the way to do that is to collect the data for calibration purposes. So, and there can be many other data that we may want to use to set up models. Depends on the complexity. Sometimes we're dealing with a very scarce data. The amount of data can be very little, but then even then we can set up the models. And this is where the physical-based models are good, because they're based on physics. Even with a little data, you will be able to produce some results that you may make some use of them. In terms of the mode of simulation, typically the models, you can run them offline or you can run them online. If you are using the models for the real-time control and operational purposes, potentially then you can connect them and run them online. Otherwise, if you're running models just to assess the impacts from different scenarios, from previous events or future events, then we would say that would be an offline mode of simulation. Duration of simulation, I mentioned before that more complex models are the models which compute the entire domain, particularly if you're dealing with a two-dimensional terrain and we have maybe high resolution, then obviously that will take a much longer time than if you would run only, let's say, 1D model without even connecting 2D models. So the size of the system, complexity, the type of the model also matters. If you're running a simplified equation like a kinematic wave as opposed to full dynamic wave, that again will take a difference in time. And then, of course, depends on our hardware that we are using to run the simulations. I will just mention quickly the different flood modeling approaches, and then we're going to break for 5 minutes. We can run the 1D model on the left side, and there is typically, if you would use and run the, let's say, EPA swing model, which you can go and download, which is a very good and convenient model. That model can run whatever scenario, and if there is a surcharge, that surcharge will be eliminated from the system, or in other words, you will not be able to see much what happens in overland flow processes. So it's only below the ground through the pipe network system or through the open channel. But then really when it comes to studying the flood, you won't be able to do much with that one unless you create another layer of a 1D model, which is the layer that provides interaction between the street and the pipe network. So you essentially set up a 1D model of the pipe network and 1D model of the street network, and then you couple them or you connect them through weirs or orifices. And then these two models basically exchange the water levels, and then when you get a surcharge from pipes, then you get the overland flows through the street 1D model. So that's something that was done in the past, but nowadays with the computational power and the software, commercial software, which is very easy to set up, people have moved, and the industry is now much more using the combination between 1D and 2D models. So which is the focus of today, to illustrate how these models are set, how they can be developed and how they can be used. So these models are coupled. So you have 1D model and the 2D model at the ground level of the 1D model nodes or manholes. And at these points, the two models exchange. There is a momentum exchange. There is exchange of the water levels. The water level comes from one model to another, and then can be interaction in both ways. If we want to look into add another complexity, particularly, let's say, if you have maybe an overflow that you really want to study the physics and how the water goes through the vertical component and spills via the overflow, then you may want to plug in the third dimension. And then if you're dealing with the modeling of the coastal system, obviously in the coastal areas, if you are concerned with the vertical axis, z-axis, which cannot be neglected, then you will, of course, use the three-dimensional model. But other than that, 1D, 2D models are pretty sufficient. So in the pipe flow models, we use the so-called Saint-Pennon equations, and these are the two equations in one-dimensional model. We solve these equations. They are partial hyperbolic equations. which typically are not solved in an analytical way, because analytically you can solve very simple cases, but in our case, what we are doing, we need to solve them numerically. So we take the numerical methods, which can be either finite difference, finite elements, or finite volumes. Typically, most of the software nowadays uses, particularly DHI software that I'm going to show today, uses the finite difference method, and then to solve these equations, you discretize your flow domain in terms of space and time, and then you could compute your propagation flood wave through this S and space and time dimensions, and then you can solve this either through typically you can solve it through either Price-Band 4-point Price-Band scheme, or like what DHI is using, Abbott 6-point Abbott scheme to solve these equations with double sweep algorithms, and then of course you can couple them with two-dimensional models, and these models, they have, besides the continuity equation, they have two momentum equations. What we see now on the screen, the short equation is the conservation of mass, and the long equation is the momentum equation. But now, if we look into the different components here of the momentum equation, we will see that the first term is the local acceleration term, the second term is a convective acceleration term, then you have pressure force, and the last two terms with S are the gravity force term and friction force term. If we would reduce this equation only to the last two variables, gravity force term and friction force, where the S naught becomes equal to SF, to the friction force term, then we end up with having the kinematic wave, and that's Manning's equation, particularly, I mean, in this case, that can be used. And then we adding another term for the pressure force term, then we move into the diffusive wave, and if you include the first two terms, acceleration terms, then we end up with having dynamic wave. Dealing with floods, obviously, that these three approximation waves are not equal. The kinematic wave will not take into account the backwater effects, and if you really want to deal with the floods and how the water propagates, then you really need to switch on the dynamic wave. You get much more accurate and proper solutions, but then the price to pay is the computational time, which obviously takes longer to solve longer equations. And as I said, for two-dimensional models, we'll have another momentum equation in y direction. Here, this one is shown to be in one-dimensional, just for x direction, but then by adding y direction, then we get the form of a two-dimensional model. So having said that, I would like to make a short break, and then we move on to the data collection for urban flood models. So please, 5 minutes, very short, toilet, whatever, water, coffee break, and then we come back.
Okay, thank you, Zoran. So yes, please come back in 5 minutes, which on my computer is about 10:53, 54. Welcome back. Zoran, I think you can continue.
Yes, thank you, Zoran. Yes, I will put the presentation mode again. Yeah, okay, and now to set up this duplicate screen, and then we are good to go. Okay, I hope it was good.
Yeah, it looks good. Yeah.
Yeah, great, thanks. Okay, now we go into the data collection. So from setting the scene about why the models are important, flood risk assessment, estimation of hazards, what kind of models, 1D, 2D, 3D models we can use, how do we deal with them, we are moving on. So now we are into the data collection for urban flood modeling. I'd like to acknowledge here that I'm using also slides which are developed together with my colleague Ole Mak, who used to work for DHI. Now he works for Kruger in Denmark. So also credits to Ole for using some of his slides. Very briefly, I will in this block of 45 or 40 minutes or so, or 35 even minutes, I will cover a few aspects of the data collection for urban flood modeling. I mentioned before that we use we need the data, geometry data, to set up our pipe network system, particularly the 1D model. We need the pipe diameters, we need the depths of manholes, the ground level, inlet level. If we have pumping stations, we need the QH curves. We need all these data to be able to set up the model, but also for 2D models, we need the spatial data, we need the terrain data, and then sometimes if we couple the land model with the, if it is a coastal area, then we may need also bathymetry data. And then we couple with 1D, with the 2D, 1D network, pipe network, for example, with the terrain data. So we need to collect all of that data, but we also need to collect the so-called temporal data, time series data, and we need to then process them all. So I'll touch upon first on the temporal or time series data, why, how, and what to measure, and then I'll talk a little bit about the spatial data collection, a little bit on the total station, using deriving data from total station measurements, or using the airborne laser survey. And then also we'll talk about a little bit about the data processing using GIS and other technologies. Again, the most of the slides that I'm showing here comes from these two books, Urban Hydroinformatics and Flood Risk and Social Justice. So the question, why data collection, temporal time series data, which is typically rainfall, water levels or Qs, the velocities or the discharges. Well, we are dealing, if we are dealing with the water systems in urban areas, utilities, we obviously don't want to have a problem with malfunctioning of our system. So we need to learn how our system works. To learn how our system works, besides knowing where the pipes are and everything else, we need to know how our system responds to dry weather flows and also to wet weather flows. We need to answer many questions as we are dealing with such data, with such systems. For example, a question that typically pops up is, do the stormwater pipes surcharge when it rains 40, 20, 30, 100 millimeters an hour? There's a typical question, because then the water managers need to know if they will block traffic in certain areas or inform public not to go in certain areas and so on. Another question that often comes to the water utilities and the urban water managers is the dealing with combined sewer overflows or sanitary sewer, separate sewer overflows. Is whether these overflow points, will they spill when it rains? What type of rain or what magnitude of rain will cause spilling? And how much that spill will get into the receiving environment? So all these questions sometimes can be answered only by looking at the time series data that's been collected from your drainage network and the rainfall stations. And by carefully analyzing, you might be able to answer some of these questions without even having to set up a numerical model. Also many other questions, because in urban areas we have the drainage networks, we have sewage networks, and then sometimes the question can be, can the sewer main hold the sewage from additional number of houses? If the planners want to expand a particular neighborhood. So all these things you can really already sense or see by analyzing the data. And there can be many other reasons. Another important thing is dealing with inflow and infiltration. And inflow, particularly if you have a separate sewer system, then inflow comes directly from maybe illegal connections or some broken pipes and things like that. So then you really want to know where to go and how to fix these problems. Or if you have infiltration, which could come from some root intrusion or displaced joints, or again, some structural problems with your sewers, you with measurements, you can pinpoint those areas. But for our discussion today, we very much need these data to calibrate our 1D and 2D models. And of course, you can use it for real-time control applications and for many, many more things. So what do we typically measure and how do we measure things? We use sensors and meters. We use structures in the pipes. We can install sometimes structures to measure the flows, or we can use the portable devices. So what is typically measured is the depth, water depth or water level, velocity, and of course, we can combine this into the quantities, into the discharges. The depth measurements, the depth of flow. We can use rulers. We can use pressure sensors, which are typically hydrostatic pressure sensors, or we can use also ultrasonic sensors, which are typically mounted on the top of the soffit point of the pipe, and then they measure the space between the soffit and the water as it rises through the pipe network system. In terms of the ruler, depth of flow stick, they are easy to use, but they are very limited, and because you cannot stay for a particular location and get the readings for hours. Obviously, you go at a particular time of the day or during the event and take some readings, but they are very limited, and of course they may not be very accurate because debris and some deposits can be in the pipes, and then when you place your ruler, then you may find a problem to read the accurate depths. So that's a very limited device. The pressure sensors, they measure the difference between the water and air pressure to determine the flow depth. The pressure sensors to work properly needs to be covered with the flow. And the readings can be drifting sometimes, we lose the accuracy, and then of course you need to recalibrate these instruments from time to time. And sometimes because the pressure here is important aspect, and in sewer systems you may have sometimes due to different gases, you can observe some pressure, and then you may need an air vent to be able to get these things in a proper way. This is an example of a pressure sensor. How can it look like? It is typically on a cable, and then you put it at the bottom of the pipe. You fix it there on a ring, and then the other part of the other end of the cable goes into your logger, and then you can install it. The problems are if there is a too low flow, then of course you will get some scattered data reading, and sometimes of course we can experience loss of power. Ultrasonic sensors can be used for depth measurement. They measure the airspace above the flow and uses the sound as its reflections. Obviously, as it uses the sound and the reflections, they may run into problems if you have sometimes road works where the workers can drill the surface and create all kinds of noise that may interfere with your readings, and that's something to be aware of. They operate ultrasonic sensor instruments. They use an ultrasonic signal, which is around 40 kilohertz, and that's not something that the humans can register, where our hearing range is between 20 hertz and 20 kilohertz. As I said, they can be affected by the noise, signal direction, and this is a typical flow meter installation where you can see that the sensor can be installed on the ring, and then the other end can go into the logger and can hang into the manhole, and then from there we can use in a wireless way to receive the data in our office, or you can come with a computer and download your data on the spot. So typical operation of ultrasonic sensor is that you have transmission and detection. So what's been measured is the airspace between the soffit, the top point of your pipe, and the water level as it rises up and goes down. Some examples on the left side, we see the ruler. I took this photo in Bangkok in one of the pumping stations they have in their sewer system. So the guys who work there, they go from time to time and take the readings, and then they note down in their system. what sort of water levels they read. So this is fixed. And then these other pictures show some of the devices for the flows. And these are the pictures, by the way, which I've taken about 15, 20 years ago when we were doing some study in Thailand. So this is the metal ring that we typically use to put this kind of instruments. And then you have a cable, and then the cable goes into the logger. And then, as I said, you can come to the site and download, or you can use the wireless system, and then you can do that. And then, of course, what we like to do when we install these kind of devices, we would like to also in the same vicinity where we have this device, we'd like to install the rain gauge, because if you're going to use this data for your model calibration, then you need obviously rainfall that is driving the flow through the sewer system, through the pipe network system, to correspond with the same timing and to be in the same area. And then we have this data that we can then play with our calibration, which we'll talk later. So the problems with ultrasonic sensor, there are many problems, of course, that potentially can happen. But if we engage experienced contractors to do that, then the problems will be minimal. We can also measure the velocity with ultrasonic Doppler meters. We can use the other devices. And typically the velocity sensor can be positioned at the bottom of this metal ring, which takes the shape of the pipe, the diameter, and then you have two crystals there. One crystal transmits the ultrasonic signal, and the other one sends the signal reflects back from the particle flowing through the water, and then what's measured is the time that the signal comes back. And that's the principle for that. We can have some. There's a different configuration for different sensors that can be positioned in different places to get the timing and to give you the velocity readings. So which equation is used to process the data? We can use the continuity, obviously, and we can use Manning's equation, which is typically used to process this kind of data. But again, if you engage a contractor who is experienced in doing that, they will give you data in whatever format and whatever you want. Sometimes we may opt to decide to install as primary devices weirs, flumes, and some other magmeters. But nowadays, I've seen many more people using the ultrasonic sensors and the velocity sensors and pressure sensors. So moving through this, I personally have worked with the ADS instruments, and there are many others you can find on the market. This is again, I put this list some time ago, but nowadays there can be many new players on the market offering their instruments. I personally worked with ADS, and I have pretty good opinion about their instruments and their work. So few things that we need to be aware of is that like with any recordings, even with cameras that we have nowadays, we have to be aware that the data storage is limited, and if we run to the end of the capacity of our storage, then it may start recording on top of it or may stop. So that we have to be aware of that and act in time to be able to have our recordings for the entire period that we want to record. Moving through this, again, what are the costs to install this type of instruments? Again, I'm pulling up some example from my past work where the installation and maintenance and everything for the first few months was quite cheap, in the order of $10,000 US. And that's really, and then of course, if you want to leave one of these instruments for whole year or 2 years, this can of course be more expensive. But again, all together, this is just a fraction of the total cost that we need to use to construct the infrastructure works. And this data is very, very important. Sometimes can help us really to understand what we are doing and what's the best to do even before we set up the numerical model. Now, the question is about how do we pick a good location to install these instruments? Because obviously it is not equally good to put these instruments in a location where you have a large head losses. For example, if you have a head loss due to elevation, where one pipe comes in a certain level and then the outgoing pipe in that manhole goes, let's say, 1.5 meters or 2 meters below. Obviously, you're going to have a large head loss there, and then that you will want to avoid it. Or if you have some maybe sharp bends where the pipe changes the angle, and also we need to be aware of if there are electrical connections, telephone connections to transmit in a wireless way through telemetry and SCADA. And of course, we need space for installation, sometimes a large space. We want to obviously avoid the broken pipes, because if there is a structural problems with the pipe network systems, we don't want to leave the instruments there, because they can obviously get stuck there. We of course need to avoid the obstructions such as rocks, or maybe there is a root intrusion from the pipes. I mentioned drop connections. If you have a heavy inflow infiltration, also you want to avoid that. Slope changes, which will again cause the change in the flow regime, coming maybe from a supercritical to subcritical, and then you have hydraulic jumps and things like that. So you want to avoid these locations, because your readings maybe will get scattered, and you get some erroneous things. When you have any place where you have velocity changes, we can cause this. Couple of words about the confined spaces. Entering sewer system is obviously a confined space, and then what we have to maintain is the safety, very important for ourselves and also colleagues who might be going there, and people who go to work in sewer systems. They always need to go through a particular training, and they need to be wearing a particular equipment on them, and they need to use also obviously the masks particularly if there is a high presence of gases there, and H2S is one of them, which is also the so-called as invisible killer. You don't see it, but then you can really get overcome by these gases, and they can be a problem. I worked for many years in New Zealand, and I've lost some of the colleagues who were. This is one of them, Ken Carew, who I like to always mention. Very experienced guy. Was in Auckland, in Auckland City. He worked there. He knew sewer system very well, but even Ken got into a problem with the gases, and he and two other guys died on the same day when they were accessing the sewer system without full equipment. Also, we need to be prepared for other things. It's always good to ventilate the sewer system. Also, I remember there was a case once that if the sewer system or the stormwater system is quite large, and then you have maybe a variable topography and kind of spatially varied rainfall goes to the city. You have in one part of the city storm, and the other part is dry. And then if you're doing maybe downstream is dry and upstream is the rainfall is happening, and you are doing some work in a sewer system, and if you don't know that that there is a flood wave coming through a sewer system, you may get flushed through, and you can get all kinds of problems. This is to be very well coordinated, and all these works really need to be carefully planned, and also with some other preparations. Manhole covers are very heavy. Obviously, we need to have proper equipment to do that, to deal with it. Another interesting feature is that this equipment needs to be intrinsically safe, meaning that they should not cause any sparks or any situations where you can get the explosion. In the past, there were some situations like that, but nowadays the manufacturers of this equipment, they often put the X mark to indicate that their equipment is intrinsically safe. Couple of words on the sampling. What else we want to collect from sewer systems and from the nearby receiving waters, open channels, is the samples that we want to analyze to see how our sewer system what does it carry? Particularly, sometimes we want to look into the first flush and to see what kind of sediment buildup and what particles we get on the roads and how that impacts on the receiving environment. In that case, we may want to collect samples, which can be either grab or composite or continuous 24-bottle sample, for example, where the beginning of the after dry period, at the beginning of and then you have wet, the rainfall event. So when you start collecting the bottles at the beginning of the storm, you may get very, very polluted waters, and then as the dilution happens, goes, then you get less and less concentration. So if you want to study and analyze the impacts from the sewer system on the receiving environment, this is very important. And for other types of ecological ecosystem monitoring. Couple of words on the rainfall measurements. Typically, we use tipping bucket rain gauge types. So these rain gauges, they have the tipping bucket, which tips when what I have here as illustration. You have two small kind of spoons, which with the rainwater goes through the funnel and fills up one spoon, which then tips and sends a signal that that particular depth has been produced, and then the other one empties and goes up, and then these two spoons sort of, one gets filled up and the one is empty, but the one gets filled up, then it empties, and the other one goes on, and then it can be really, really interchangeably and very frequently going up and down depending on the magnitude and the intensity of the rain. Couple of words on the if you have a large network and if you don't have these obstructions that I talked about in terms of the structural integrity of the pipes, or if you don't have and if you really look to avoid these sudden velocity changes in the system, you will also want to look into the strategic positioning of your flow gauges. This is an example of a catchment where the green lines represent the pipe network system which has been modeled. The light gray lines and the dots represent the pipes and the manholes which have been omitted, because when we build 1D model, we never use every single pipe to model. We always like to simplify the network for several reasons. And what you see here, the green lines represent the pipe network system which has been used, built into the model. But then the question comes, if I want to calibrate my model, where do I position my flow gauge? If I have budget just for one location, then I would obviously go right at the end to the outlet pipe location. What you see is the rectangle in the light blue color, so that's the outlet of this system. If I have a budget just for one place to put the flow gauge and maybe rain gauge somewhere in the vicinity or in the middle of this catchment, I would choose that option, and then I would use that data for calibration of this model. If my budget is larger, then obviously I would try to break this pipe network into different segments and maybe isolate and monitor some catchments, some lead catchments, and also if you have some problems, known problems, flood-related problems or overflow, then you would also want to isolate and do more monitoring in those areas. But this is really a strategic question in terms of positioning. Then it comes the question about what's the structural integrity of the pipes, condition of the pipes, and also are the flow conditions good at these locations? If not, then you need to go maybe a little bit upstream or downstream to seek a proper location. This slide here shows that in terms of the rainfall measurements, we have to be aware of that the rainfall can be very much a variable in urban areas. Sometimes in urban areas depends on the location, on the local characteristics, can experience a really different storm patterns. What I have here is one of the catchments in Australia called Belmore South, where the three triangles represent the three rainfall stations, and the three time series plots represent the station, first station, second and third. And what we can observe here is that the first station did not pick on some of the rainfall events that the station 2 and 3 have picked up on. So the consequence of using one of these, for example, the one on the top, would mean that using this data, rainfall data, to calibrate your model, would mean that you would be wondering, where is my rainfall? If you measure the flow through the system, and then you get flow response to the measurements taken by the rain gauge station 2 and 3, the one in the middle and the one below, you won't be able to reproduce that response to your system, because if you're using only the one measurement, the measurements from the top rain gauge station. So this shows the importance of having sufficient number of rain gauge stations so that we can have a more successful calibration and better representation of the spatial variation of rainfall through the urban area. Now I'm going to jump into we have another 10 minutes. I'd like to spend a few words about the spatial data collection, which is very important, particularly when you want to set up two-dimensional models. I mentioned before, for one-dimensional models, we deal with pipe network systems, typically in urban areas, where we need, for every manhole or node, we need X and Y coordinates, and then we need, of course, the Z value, which is the ground level and inlet level. We need pipe diameters. All this geometry data is important. We put it into 1D model. Now we go to the 2D model. How do we go about data collection? Well, we deal with terrain data, and there are different ways to do that. What you see here is that in urban areas we also have different obstructions to the flow. So when the streets fill up with the water, depends on the curb heights. The water may stay confined, and of course on the intensity and the amount of rain, the water may stay confined to the curb network and flow in parallel with a pipe system, which is typically under the roads. And then when the water exceeds the curbs, then it will spill around. And then could be other aspects that we need to be aware of. So we can do the ground surveys, obviously, which is a traditional way of using the total station. Level station and things like that. We can collect the data, and then we start typically from one point and go around urban area, and then we may find at the end that we have a particular error, which then gets typically distributed to different points, and we complete our survey, and we have a point data, which is XYZ data. The other thing which is nowadays been used a lot, and it's not too expensive, quite affordable, is to perform the airborne laser survey data collection using the LiDAR, light detection and ranging, which is typically the equipment that gets mounted on a fixed or rotating wing aircraft, which flies low. And then on board you have the inertial measurement unit. GPS is very important because it tracks the position of the aircraft. And then obviously we need a LiDAR scanner, which sends the laser pulse to the signal to the ground, and then measures the reflectance from different surfaces. We'll have different reflectance. So the guy who does that will come back to the office with a point cloud data. So the point cloud data then needs to be carefully filtered. So the data can be really collected in so many flying along the scan lines and collecting in every second large amounts of data. So what we need to typically do, because we're dealing with a flood management or flood modeling, we don't need to know the height of morphological objects, trees, bushes, and things like that. So what the person who is collecting this data needs to do is to perform morphological filtering. And then perhaps you may also want to avoid the heights of the buildings, because dealing with the floods, we may not need to know the heights of the buildings. It may be sufficient for us to use only the bare earth data sometimes. And then obviously we need to interpolate when we extract this object. We need to interpolate in between, and that's typically done by the contractor who does that. And then we may get something like this, which we can use as a basis for our two-dimensional model. And then that model, the intention is to couple it with a pipe network or open channel model, which the two together would in conjunction produce the water depths and velocities that we can then project into our maps or 3D visualizations. I mentioned before that the pipes are very important, pipe network system. So we measure the diameters, we measure the inlet level of the outgoing pipe and the incoming in terms of where it comes into the manhole. Is it at the bottom of the manhole or comes a little bit higher than that? Is there any internal or external drop? So all this information is very important because it will generate a different situation when we run the model. If there is a large drop, obviously we're going to have a large head loss, and as opposed to if we have a very smooth transition from one pipe to another going through a manhole, which has a proper benching done at the bottom. So in terms of the pipes, we need obviously pipe diameters, if it is a circular pipe, or we have a proper dimensions, if it is a rectangular X shape, and we need to put it into the model. For the manholes, we need the ground level, inlet level, manhole diameter. If the pipes are up to 1 meter, they would typically have the manhole, the diameter would be standard, which is 1 meter. And if it is pipes are larger, there may be some chambers and can be quite deep. So in that case, we need to get all these dimensions because they will act also as storage units in our pipe network system. Pumping stations are also very often a part of our urban drainage network. And for those, we need to know the wet well, dry well, the wet well dimensions, what's the storage there, where is the inlet, and all of course, the pump characteristics, QH, head and flow relationships that we normally would put into our 1D model. Another important thing to consider when we collect the data for the 1D, 2D models is the number of gully pots or catch pits or or catch basins, whatever you call it, is to see the efficacy and how the water from the streets will get into your pipe network system so that you can potentially set it up in your numerical model. Another important aspect is the overflow structure, and then sometimes we may have combined sewer system, we have separate sewer system, the water may go from one part to another, and these heights and all this information is important to know. And then finally, outlets. We need to know the outlet, at which level is the outlet, and also we need to know if that outlet goes into a receiving water, where is the water level of the receiving water, because this will form your boundary condition for your one-dimensional model, which is very important, again, to get a good representation. Besides the pipes, we may have the culverts and channels. In some urban areas, we may deal with open channels. So you may have a heterogeneous network in the sense of the closed conduits and open channels. And then when you have open channels, you may have also the culverts and the bridges, which can sometimes act as impose serious restrictions to the flows. And that's very important, again, to be incorporated into the one-dimensional model. So these type of structures we typically put into pipe networks, open channels, including the culverts and channel and the bridges. We would normally put it into the 1D model, and then we would couple that 1D model with a 2D model. So the 2D model computes only the overland flows and the surface. If we have some retention or detention basins, which act as part of our drainage network, obviously we would like to know that. And that can be also incorporated and typically can be done also in 2D model, but traditionally we would normally incorporate this into the 1D model. And you can find different kinds of storage. This is an example of a sports field, which acts as a flood storage. This is in Porto Alegre in Brazil. This is in, I took this photo, this is in Denmark. Similar thing with embankment around the sports field, which acts as a storage. Another important aspect when we do the data collection is to look into the condition assessment of our drainage network. Our pipes can be quite old and can be deteriorated in terms of the quality, and that will directly reflect the water values for our roughness coefficients we want to use for our 1D model channel. whether it is a pipe network or open channel network, we need to perform some inspections. Sometimes to do that, we need to use the CCTV cameras and run them through the pipe network system, or go and do the visual inspections if it is the open channel network, and then try to work out what would be the most appropriate roughness value that we want to put it. Another thing to be very much aware of, and coming from the practice, I've seen many cases where people illegally connect their household pipes. And particularly if you have a separate sewer system, maybe in a sanitary sewer, they connect their rainfall pipes, and then you may spot this kind of structures. And then when you measure the flow, you may see a rapid response to the rainfall, which will indicate you have some direct inflow, and then that's important piece of information for the models. Sometimes the condition of your pipes can be deteriorated to the point that you simply cannot, no roughness coefficient will help you there. So then you really need to take into consideration that the network is in a deteriorated stage, and then you need to. So what I'm trying to say here is we need to, besides setting up the data, collecting the data from the field, we also need to do field visits and observations to see if there is anything particular that we need to pay attention and set up the models. And this comes to the end of the setting the scene of the flood modeling, and looking a little bit into the talking about what kind of models can we use. And I mentioned 1D, 2D, 3D. And I also mentioned, I went through the time series data, temporal data, and also spatial data that we need, including the data for the 1D model, which is the geometry of the pipe network and the open channel network, and also for the 2D model, which is the terrain data. So now we're going to have another break, and I think there is a time now for Q&A, and I'm happy to try to answer questions that you may have. And after that, after the lunch break, we'll go into the. I will show you example how the 1D 2D model was produced for the city of Dhaka in Bangladesh, where we have some nice data, and I'll take you through the menus, even how the model is configured in the mic software, so that potentially in our summer course, if some of you come to the Netherlands, we will be able to show you how to do that by yourself. So Zoran, over to you, Zoran. So
okay. Thank you very much, Zoran, for a very nice, interesting, and very comprehensive lecture on these issues. I'm just wondering, given that we have a forthcoming lunch break at 12 o'clock, maybe we can just press on with Q&A session now without any short break. Is that okay with you?
No need for a short break. Yeah, the short break.
Other participants can take the break if they want to. I mean, obviously.
Yes.
Okay, so we'll now start the Q&A session. You can ask Zoran any question about what you just heard or otherwise. When you ask the question, please raise the hand when you want to ask the question. And then when you start asking, please switch on the camera and the microphone, obviously, and state your name and affiliation so that we know who are you. So as of now, you can ask any questions. We don't have any at the minute. I have one to start with. So you talked a lot about data, different data sources, and why it's important and so on. Given your experience from working in multiple countries, leading these large research projects, where can you typically find this data? What are the good locations, the websites, the types of websites where you can find different pieces of information? And if you can't find it there, what are the organizations you need to talk to in order to obtain data?
Yes, data is always a challenge, and it's never enough of the data that we collect. So we always, whatever amount of data is available, we would like to have something more in addition to it. But the basics is that we get connected to the water utilities, who would typically have in their asset management systems or GIS systems the information about their networks, which is then used to set up 1D models. My experience is that this data needs to be should not be taken for granted, even though that they are operated by the utilities. You may sometimes plot this data and you get some kind of adverse either pipe diameters or the slopes going up and down and things like that. So these things no water utility is prone to that, to having this kind of question marks, whether that's really the case. Sometimes is the case, sometimes not, but typically would go to the utilities, collect the data, and then QA it, perform the quality QA kind of assessment to see if the data has some question marks. They need to be double checked in the field, and then we would go to the field, either ask them or we go to the field to look into that and to confirm that indeed there is an adverse pipe diameter there. So going from a smaller diameter to the larger, back to the smaller, or going having negative grades. So that's typical thing. So that really requires quite some time to even though the data may be available with the utility, it requires time to QA it, to make sure that the data is really what we get is safe to be put into the model. So that's about the geometry of the system. When it comes to the topography, in some places, some utilities, they run their either spot elevation measurements, and they have some kind of topography. They have a contour maps. Sometimes we start from the contour maps and then interpolate. You can do that to create the raster map in GIS, and then typically the raster is conveniently used to set up a 2D model. If that doesn't exist, then obviously you need to engage someone to do that kind of work, because for two-dimensional models, you need the terrain data, and that would need to be collected either through the spot elevations or airborne laser survey, what I just mentioned. When it comes to the sometimes like it used to be one of the sources to collect this terrain data was the SRTM, I think, website, and then you can find maybe some other, but they have typically coarse resolution. You may get the data of 30 meters cells, which for urban flood modeling applications, this is not really much of use.
Yeah, but there are some publicly available websites in some countries where you can download at least the data to start with, the digital terrain data.
Exactly. So the publicly available data might be of not sufficient use, and I can show example very briefly, or the problem with having the data, which is this is an example of a model, just of a model simulation result. I'll duplicate the slideshow. You may have one thing is to collect the data, but then it's to verify with the objects on the ground, particularly in urban areas. In urban areas, you can have all kinds of problems. You can have narrow passages between the buildings that the conventional LiDAR data will not be able to pick up. If you have, let's say, 0.5 meter gap between the two buildings, which will allow water to come from one side to the other. But if you're aiming for 1 meter spatial resolution, your LiDAR guy will not provide you with that gap in between. And then you may get a totally different flood map from the map where you can open these gaps. So on the left side is a conventional LiDAR, which shows more of the dry areas compared to the right side, which is here we use structure for motion technique, where we ran the survey through the city, taking the photographies along so the camera would be mounted on the car. Sometimes you can do it with drones as well, and then you run the vehicle through the city. You collect this information about these gaps, and you go and correct your LiDAR data, and then your model will produce potentially totally different result. And this is the case where we are. This is in Thailand. Ayutthaya is the location where we produce the data using the conventional LiDAR data, and then we've cleaned this data, the terrain data I'm talking about here, with the structure for motion, and then you can get totally different flood map. And then we talked about the resolution just now, and this is an example. If you have of a particular, let's say 7 hectares area in urban area where you have some buildings, you have curbs, higher buildings, lower buildings. And this is 1 meter grid size. So what we can see here, the 1 meter grid size, and typically we would use that as a 2D model basis. So you can see the curves. So if the terrain is flat, like here, when the rainfall amount exceeds the capacity of sewer system, then you may get the flows through the roads, and the water gets confined to the curbs, and then when it fills up, starts to spill around the buildings. But that's very important. When you have 1 meter, you can capture that. When you have a 2 meter grid size, you already smear off these edges. And then this is the same area, just with a 2 meter grid size. And then we move on to 4 meters, then you can see the effect of the curbs totally disappears. And then the 2D model will compute the water going left and right without being confined. And then you already introduce uncertainty in your result much more. And then we go to 8 meter grid size, then the smearing off becomes even more profitable. And then you go 16, you see that a lot of buildings disappear. 32 meters totally, you get something which is useless for urban flood modeling work. So this is about the data, terrain data for 2D models, very important. We can collect it by the spot elevations or airborne laser survey, but then even then it needs to be properly prepared, or otherwise you may run into these problems. And then temporal data, this time series data measurements. If you're dealing with the area where you can have lots of measurement points, then it's a luxury. Then you can calibrate your model. If you don't have anything, then you really should do some installations and collect some data. Try to calibrate the model.
Okay, thank you, Zoran. We have a question from Kaushik Mandal. Kaushik, you managed to type your question in the chat, but perhaps it's better if you just ask rather than me reading what you put in the chat. Yeah, just switch on your microphone and ask the question. Yeah.
Hello, can you hear me?
Yeah, we can hear you. Please go ahead.
Okay. First of all, thank you, Professor Zoran, for your wonderful experience of your lecture about the hydrodynamic 2D flat modeling. So my question is like, in my master's thesis, because you mentioned the National Chiang Kong University, I was actually graduated from National Chiang Kong University this semester, in the last semester. So in my master thesis, I ran the 2D hydrodynamic modeling in Delft 3D FM. So for my case, I face like the computation time takes too much time for my study area, because in my study area, both the upstream and downstream boundary condition is 10 kilometers far away from my study area. So every time when I run the simulation, it takes like more than 2 days, 3 days. And in my initial time, I thought like it might be the computer problem or something. Then I checked the computer setting was good, but I don't understand why it takes too much time for to run the model, especially if the boundary condition is little bit far from the study area. So have you experienced before like this, if the boundary condition is far from the study area?
Yes, thank you, Kaushik, for your compliments about the lecture. It's very difficult to judge that, but maybe what's the model that you're running? You said NCKU. I mean, I know they have even their own models. They have quasi-dynamic model called PhD model. I have a student who has been working on that, but that's a very fast computing model. But I don't know what kind of model did you run?
The Flow FM in Delft 3D FM.
Delft 3D.
In Delft 3D. Yeah. I use the Delft 3D in Flow FM, the 2D hydrodynamic modeling.
Yeah. And you also coupling with something below ground, or it's only the
Also, I include the both discharge, water level, and bathymetry, and also the channel geometry.
And what's the area, total area that your model domain covers?
Because my model, I study in a meandering channel in Ganges River in India actually, So the study area was around 13 kilometer. The
And
13 kilometer mean
what's the resolution of your
the
2D model?
you mean
the resolution of your 2D model? Like if you're, is it the what kind of, is it the rectangular grid or
oh yeah it's a in Delft 3D FM they use the I think curvilinear grid and
building? Yes. And how many of these cells are there? How many of these computational
okay
cells?
because I remember because I run the model in different years, like from 2001 to 2022 in 6 years bathymetry data and change the water level and
And you're running
discharge.
You're running the series?
Every year, yeah, I run every year, but I think I remember because for every year I change the channel geometry is changed for river. So every year I make the new channel geometry and my cell size is different for every year. So roughly it's more than 20,000 cell, I think, for that study area.
20,000 cells.
Yeah, 20,000.
And your simulation event, that event that you're simulating, is it one event or multiple events? Is it continuous for years?
No, initially I run like for a long term, like 2 years, 3 years continuous. But it takes like I remember like for 3 years I run.
Yes.
It takes 20 days. It takes 20 days, and I thought, oh God. And then I asked my professor, and he told me, okay, then you can reduce the time limit, and then we just make it separate year with the different cells. We change the cells, and each year we run the model and then it takes 1 day or something like 1 day and happen
There can be
6
many
hours.
factors. There can be many factors. Of course, if you, I mean, one thing is you have a lot of cells, computational cells there. Then of course, so it's that's one thing. Another thing is if you're running long-term simulations, if you're running continuous 1 or 2 years, and the year has dry periods, has a small events, has medium, large events, and again all of that. So running instead of just one single event, then of course you're going to have it's going to take time, and then I don't know, for example, what sort of time steps you're running there and things like that, and then that can also cause a certain computation.
Yeah. Time step, I know.
And the hardware. So all these things together will give you a challenge to run these complex models, and it will take time. That's what it is. What I'm showing here, I'm showing pretty much the simulations for one single event. So it's the event that takes a few hours, and that's it.
Oh yeah.
And even that can take for some of these models that I'm showing today, it will take a couple of hours to compute because So it's unfortunately that's the nature of this type of physical-based models with a large number of cells, and if you run the long-term simulations with so many different events, then obviously, and then of course another thing to watch is that I don't know if sometimes you may have some computational instabilities and maybe model will not crash.
Stable, crash. Yeah, sometimes I also face this problem. Like some days when I run the model, some days the model data is not good. Sometimes it's missing. So
but maybe you need to try to first run for a few events at a time, and then you see if your model gives you. I mean, running a model for long-term sort of series is good for statistics. I mean, I would say statistical kind of analysis of the impacts and things like that. Like you say, okay, in 10 years we had so many flood events, we had so much of has been flooded and things like that. But if you're running for the flood kind of modeling purpose, so it's a stormwater modeling, then you may want to, I don't know. I mean, of course, obviously your supervisor will direct you what to do, but you may want to run individually small event in medium or large events, like one in 5 years, one in 20 years, one in 50, one in 100 years, and maybe and then you process it. Because if you run this long-term series, then you will really face long computational times.
Because I already graduate and I faced this problem during my master's thesis time. So I have like my query is like, how do you usually consider the computation time for this kind of modeling actually? Because no one gives the proper advice like you takes like this time or this time. So is it any?
Yeah, no one can give you precise time estimate. It's depends on the complexity of the model. Depends. Sometimes you may your simulation, as I said, can be unstable, and the model is trying to stabilize it, and it takes forever to compute to try to get through that, rather than crashing. But it's just turning around and halving the time steps and halving, reducing. So. No one can tell you exactly how every case is different, every setup is different. But if you come next year in the summer to Delft, we can look into your model.
Okay. Oh, okay.
Yes,
okay.
Indeed. And there is an alternative of AI-based models which produce much faster computations with some loss of accuracy, but hopefully not too much. And that's what we will be doing in the summer school in Delft as well.
But okay, so I have another question about the summer school, because I already graduated this September from the National Chiang Kong University in Taiwan. So can I join the summer school after graduation? Because I am now looking for job actually in both Taiwan and other country. So is it the fresh graduate can join the summer school?
As far as we are concerned, you can. I mean, Veljko may give you a more precise answer, but this is, we don't have an age limit or any other constraint in that sense. If you're interested in the topic, want to learn more, it doesn't matter if you graduated or not, if you are an MSc student or not, and so on.
Okay, yes. Okay, no problem.
Come to Delft. We'd love to see you, meet you there, and talk about your...
Okay. Maybe I will email you personally later.
We'll spend a couple of days in the school, first on this physics-based modeling, but then the next 2 days will be on data-driven modeling, on AI-based modeling.
Okay.
So you will learn how you can speed up the calculations quite a lot, by orders of magnitude, if necessary. Okay, do we have any other questions?
Thank you.
Thank you very much for the question. And yes, Milan Group, please ask the question.
Hello, my name is Milan, and I'm a junior researcher at Institute for Artificial Intelligence of Serbia, and also PhD student at Faculty of Electronic Engineering, University of Niš. Thank you for interesting lecture about data operation. And I have a question about the modeling drainage system. You mentioned that the physical parameters of drainage system, such as pipe length or diameter, is very important. And my question is, if we replace a physical model with some kind of neural network model with hybrid or graph architecture, do you have any idea how actually we can incorporate these physical parameters, such as pipe length or the diameter, into this neural network model?
Neural network model works, as we all know, on the basis of input-output data. So there's no physics in between. It can talking about the neural network model, unless you go to physics-informed neural network models, which is a different kind of neural network models. But if you go to the standard ANN, obviously you will train your model, let's say for rainfall and the flow through your pipe network system. You will train your model, and you can pick different locations in your pipe network system, and then to represent that particular network. The moment you change a pipe in your system, or maybe the characteristics of your pipe network systems change. Let's say there is a buildup of sediments, and then the diameter becomes smaller, whereas your measurements and training that you used was before that change. Then obviously you will need to do new round of measurements and retrain that. But the entire geometry of the system in response to the rainfall is taken into account through these input-output measurements. So because obviously in an urban network you may have, I don't know, you may have for a very small catchment maybe 50 or 500 pipes. In a larger catchment maybe you can have 5,000 or 10,000 pipes. So all that collective hydraulic situation within your network, given the pipe diameters and the levels, and it is taken into account by the measurements of input-output. But single pipe, I don't think you can, unless you measure at one particular location, I don't think you can capture that. Neither you would want to do this.
Yeah, maybe I can add something to this, because we have been developing models at TU Delft before Artifact project, and now during Artifact. These are GNN-based, graph neural network-based models. And we did use, in addition to the inputs that Zoran was just mentioning, we did use pipe diameters and a few other variables as inputs, which makes the list then grow quite a bit. But we did this deliberately because we wanted to develop a meta model that can be used, that can be coupled with optimization for the optimal design, during which, alternative solutions are being tested with different diameters and so on. So you could extend the list of outputs into the neural network, but that the network will grow in its size and complexity to match that increasing number of inputs. And you have to be very careful with the type of machine learning method, because traditional artificial neural networks may not do as well as some form of deep learning and so on. Okay, any other questions or follow-up question, Milan? No?
No, thank you for response.
Thank you.
We
have time left for one last question before lunch break. This is a unique opportunity to ask Zoran questions. He's normally charging a lot of money when he does this for some industrial partners. Yes. If not, I guess we can break for lunch now.
Yes.
There will be an opportunity for the next Q&A session after the other session, and that one will be a bit more with the examples and may raise a few more
we'll go
issues.
to of modeling and I'll show the case studies.
So let's break now. Thank you, Zoran, for all the talk, and thank you for all those who asked the question. Let's break now, and please come back at 12:30. We'll start exactly on time. Yeah.
Great. Okay. Thanks all. See you soon.
Well, welcome back, everyone. We'll continue with the expert training event. Zoran has more stuff to share with us. So over to you, Zoran, when you're ready. Just
yes. I'm just switching the screen. So I hope you can see my screen now.
Yes.
I'll just wrap up quick what we've gone through today. We've talked a little bit about the purpose of using the models, physical-based models for the flood risk assessment, which is very much for the hazards. And then we also talked a little bit about the different forms of modeling that can be applied for that purpose, which is one-dimensional, two-dimensional. You can even, if you want to include a third-dimensional model. But then we heard before from Kaushik that how computation expensive are two-dimensional and coupled 1D, 2D models are. And then if you switch on even the third dimension, then it becomes even more time-consuming and more complex. And then we talked about the data collection for the geometry of the system and also for the spatial data. I'd like to mention a couple more things about the data to conclude this a little bit. This is one of my PhD students from Malaysia, from University Putra, who graduated at IHE and TU Delft. He did in his research work. He dealt very much with airborne laser surveys and looking into the data collected from lidars. How good are the algorithms that are used to filter different objects? So what you see here is a different DTM produced with different lidar filtering algorithms, because you obviously collect a lot of data points. A lidar contractor will collect the data points and then point cloud data. Then he or she will go to the office, filter different objects, and then will apply some of these filtering algorithms. These are some of the commercial algorithms that you can see here, 9 of them. So my student back then, but nowadays he's a full professor at the University Putra, Malaysia. He applied these algorithms for the purpose of flood modeling in Kuala Lumpur, modeling the Klang River and urban area. So now you can see that he coupled 1D and 2D models, and so basically 1D model is the same in all these 5 different simulation results that you see here. What's been varied here is the DTM or the 2D model setup, because he's here used 5 different LiDAR filtering algorithms which are commercially available, and then he had coupled these DTMs with the river and the drainage system model, and then he produced some flood maps. So what we can conclude from here, what we can observe, is that the flood maps differ quite a bit using different LiDAR filtering algorithms. And what he concluded is that none of these algorithms is really fully suitable for the flood modeling. Of course, depending on the terrain configuration, complexities, features in urban area, some of them will be more sensitive, some will be less sensitive to pick up some of these different shapes. So potentially you may run, if you have different LiDAR filtering algorithm applied to the same catchment and another LiDAR filtering algorithm, you may potentially run into different flood maps. This is something to be aware of, and to potentially look into some alternative algorithms. What my student back then did, he worked on his own algorithm that he claimed later that it works better than any of these commercial algorithms. This is just something to look at. I mentioned about the gaps between the buildings, and this is another PhD student that we had from Thailand, Vojinovic Mesuk, who works for Hydro Informatics Institute in Bangkok. He worked with the structure for motion. So the idea here was, and that was back in 2011, 12, 13, immediately following the Great Thailand floods. What he did, he used first the bike, then the car, and then drone, where he would mount the camera, and then he would basically improve the LiDAR data taken from the air. So what you see now here, for example, in Thailand, when you have this kind of structure, if you take the data taken, LiDAR data taken from the air, from the aircraft, then you will get a block of a house. And obviously, if you take that straight into your 2D model, you will have an obstruction to your flow. Whereas if you actually look, when you drive along the road, you will observe that actually this is a pillar house, which allows flow underneath. So, and there can be different objects that can cause this kind of problem. This is a summary of that. So you can see that this arc, for example, structure here, which taken from the air can close completely the space, whereas the water can go underneath. Sometimes the very dense morphological objects can also cause a bit of errors there, or can block off some spaces, which is this B. C is the narrow passages between the buildings. So what you see here also is that if you're aiming for 1 meter DTM, and then this is a half a meter or less, then obviously your DTM LiDAR work will not pick up these small gaps, and then you will get, again, if you take that into your straight into your 2D model, then you will get a fully blocked areas. And of course, what is quite common in Asia are the sky trains. So the sky trains, if you don't really process them properly, then you will get some kind of like a Chinese walls. Whatever the case is, that we have to be careful with our DTM data. If you take them straight from the conventional LiDAR processing, we may get with a block. We may end up with a block which will obstruct the flow in a 2D model. Whereas in the actual fact, the water will flow around these buildings and cause flood areas in different regions. But if you apply structure for motion, for example, to clean this, to open these gaps, to identify these passages, and then you clear it, then you may get a more realistic flood maps. Also, what's interesting to do is when we deal with the calibration, and I'm going to talk in a moment about the model calibration before I get into the other part of the 2D model setup, is one of the biggest challenges with 2D models is how to calibrate it. But before I talk about that, I'll briefly talk about the general process of calibration. And just one moment. Let me just find this particular slides that I want to show. And yes, yeah. Sorry. Yeah, here. Let's put this somewhere here. If we collect data for flood modeling, then obviously we need to have the rainfall and the flows taken at the same time, and then we need to compare the data. And this is the slide I was looking for. Speaking of the model calibration, which is very important. Model calibration is very important activity, because if we don't calibrate our model, we potentially can either overestimate or grossly underestimate your flood depths, which may lead into suboptimal design of your flood protection structures and even can create some further problems. So model calibration. So what is a model calibration? Model calibration is a process of adjusting model parameters. And speaking of the 1D models, we have obviously the hydraulic parameters, like surface roughness in our pipes, but also we have hydrological parameters. And then hydrological models, they have their own uncertainties. They carry, some of the parameters carry large uncertainties, degree of uncertainty, some of them smaller degree, but this all propagates the uncertainty and creates a difficulty to go with a particular set of parameter values. So in that case, we aim to perform the measurements and then dedicate one particular set as a calibration data set and the other set as a verification data set. And then the idea is to try to match the two curves. And then let's suppose you have your model blue and the gauge, which is a kind of fuchsia color. You may get, maybe on small flows, you get a good match between your model and the measurements, but then for some intermediate and larger flows, maybe you have more problems. And then the idea is to adjust the model parameters so that you get more perfect fit. And then the question comes, when is enough to stop your calibration process? Well, depending on your objectives, depending on your error, degree of error, because the error here is the measurement minus model, for example, or the error differences, which you need to compute through some statistical techniques or like root mean square error or mean absolute error or any of these kind of correlation coefficients. And then you come up with a certain value like 60% accuracy or 80% accuracy, then you may decide to stop your calibration process. But in urban networks, we have often combination of flows, dry weather flow and wet weather flow. So dry weather flow is a domestic or population-related flow, or even industry-related flow. So it is that the number of people who live in a catchment, you multiply by the wastewater production per person per day, let's say 150 or 200 liters per person per day. Then you get the basic dry weather flow, which then which goes through the diurnal pattern, creates 24-hour profile. And this is what we see here is the 1, 2, 3, 4, 5, 6, 7. 1 week of the blue shows in the upper graph shows the discharge, and the yellow line shows the model. So the blue is the measurements, and the yellow line shows the model results. And then you can also plot velocities and depths, and then you observe to see what's going on and whether your model is good or not. So if you're dealing with this kind of networks with the combined sewer systems, then you would first attempt to do the proper, as best as you can, calibration with your dry weather flows, and then you go to the wet weather flows, which is the rainfall-driven response in the system. So the red here shows the rainfall, and then the blue shows the measurements, and the yellow shows the model prediction. The blue is the discharge. The green is this is a real-world case from one of the catchments that we worked in, that was in Australia, and the blue is light blue is the depth. So obviously the velocity here is not quite is too high, for example. So then the objective would be to play with the roughness coefficients in those pipes which are leading to this point where the measurement is. And then, of course, we can detect different kinds of biases. Can be seasonal variation, bias related. So, for example, your model may be predicting well in one season, but not very well in the other season. So then you need to work with maybe base flows, with the groundwater infiltration aspects, or you maybe have a kind of a magnitude bias. The plot below shows a magnitude. So it's for a certain magnitude of responses, you may be either undershooting or overshooting, maybe not showing well, but for the other, like here, this illustration shows that for smaller flows, maybe the model predicts well, but then you need to still perform that. And then the question comes, what kind of statistical error functions you can use? The classic ones are root mean square error. I mentioned before coefficient of efficiency, Pearson's coefficient, and so on. Usually we would like to pick a few of those and then analyze the quality of our calibration work. So the calibration procedure for hydrological part of the model is to adjust the mass balance, area initial loss, for example, depending on the hydrological model, the timing of the peaks, and then you come to the actually to the pipe flow modeling or hydraulic calibration, which looking very much into your into the surface roughness and looking to the head losses and things like that. So that's about the calibration business, and I would now like to touch upon a little bit on the actual model setup, and then we'll go into the case studies. So the model setup process can go through different steps. I will just show you a typical sequence. Is that, of course, we need to understand the project objectives. Why are we doing it? What's the purpose? Is it that we are setting up a model for real-time control or maybe early warning purposes, or we are setting up the model to do some simulations, to run some scenarios and to look at some maybe potentially design of measures. So that will drive obviously the degree resolution of the data you need to collect and what types of models. Then it's always very valuable to perform site visits and to get familiar with the areas that you are turning from the reality into the digital twin. Then we collect the data, what we talked before. Again, I like to emphasize coming back to the project objectives before you choose a model. Are you going to are you just designing maybe a new pipe network system, which maybe 1D model is good enough, or are you looking at the existing system performance, and then you obviously, in terms of floods, then you need to deal with 1D, 2D model. Then once when you choose your model, then you need to perform the catchment delineation in terms of sub-catchment boundaries, set up the hydrological and hydraulic model, maybe pollution. They need to perform data cleanup. We talked before in the first break for the questions. We talked about the need to perform the QA analysis of the data that you get from the water utilities, and then we perform calibration and validation or verification that I just talked about, which means that you adjust your model parameters for one series, for one period in a year, let's say 6 months or whatever you have measured, and then for the other maybe 6 months you try to verify or validate your model, and then if no good, then you have to go back and try to improve your calibration parameters. And then once when you say that you have satisfied all your statistical measures, then you say that okay, now my model is fit for purpose. I can start running the simulation results. And I will quickly show you the steps, the modeling steps. First, we need to understand what's the catchment boundary. GIS is very convenient. If you have hilly terrains, it is a very quick way to obtain the catchment, overall catchment boundary, and also sub-catchment boundaries. It is not very easy and straightforward and very automated process if you have flat terrains like what we have in the Netherlands, or perhaps in I mentioned before some work in Thailand, so Bangkok is quite flat. Even Dhaka, that I'm going to talk very soon, is very flat. In these kind of regions, then you need to really perform a lot of manual adjustments to make sure that your sub-catchment boundaries fit. But if you have hilly terrains, then the GIS is pretty straightforward, can tell you what's the overall catchment boundary, looking top down. Maybe that is the area. The next step is to perform further delineation of sub-catchments, and this is the sub-catchment boundaries, because what we do, we try to split the entire area into smaller units, where we look into the hydrologies for these different units, and they are all lumped hydrological models, but then effectively, because there are so many of them, they kind of in a way mimic the distributed functionality through or behavior through the system. So this is a top-down view of the sub-catchments potential. You can have some of them smaller, bigger, depends on the resolution, where you want to go to a higher resolution in terms of the catchment delineation or course. Then you put on top your network, either open channel or pipes. Here, this is open channel. And then you set up your branches, if it is the open channel network. Look into the sub-catchments, look into the hydrological properties like percentage of perviousness, imperviousness, slopes, things like that. And then you set it up for each of the catchments. This is from C1 to O to C whatever. And then you look into your channel network. And then you need to define the loading points. And that's pretty much it, what you need for the open channels. If you look into the pipes, I will quickly jump into the pipes. Well, before I jump into the pipes, what's very important is that if you're dealing with the open channel network, you have to think about the resolution in terms of your cross-sectional areas of your open channel network. In other words, that if you, let's suppose this dashed line represents the terrain topography, and then if I would have only two cross-sections, one upper and one lower, what's going to happen? The model is going to interpolate in between the water levels computed, and then if I have irregular topography going up and down, I may create unrealistically low water depths or unrealistically high water depths, and then it's a problem if you want to project this data. But of course, when you have a 2D model, the 2D model would kind of take care of it. But if you're running only 1D model, then it's a problem. But then to overcome this problem, you need to introduce many more cross-sectional points to capture all these terrain irregularities in order to get more realistic water depths. So this is for the open channels. And then if you go to for the pipes, the procedure is pretty much the same as for the open channels. So we start with a catchment boundary, we delineate into sub-catchments, and then we overlay our pipe network system conveniently in GIS. The red dots represent the nodes or the manholes, and the black lines represent the pipe network. And then what we need to do, obviously, when we set up the 1D model, we need to give the unique IDs for each and every element of our pipe network system. So every manhole should have a unique ID in a database, so MH1, MH2, for example, or it can be all kinds of combinations of letters and numbers. And then after that, we need to delineate or define our sub-catchment properties, same as for the open channel. So we end up with different sets of different parameters in terms of hydrology. And then the next thing is to define the loading points for these sub-catchments in terms of the which parts of our pipe network system will receive flows, which is your upstream boundary condition, and then you need to set up the downstream boundary condition. So these are the steps, and then you end up with having a a model, 1D model. And now I'm going to jump into the case of Dhaka. To take you through the steps of how to set up 2D model. This is I had a stream of students coming from Dhaka, and this is one of them who did some work, collected Farhana Ahmed, who collected some interesting data, and we've worked with that. We now have a very interesting exercise, I would say, and for those colleagues who would come in a summer for our summer school to Delft, we'll be actually working on this actual case, setting up the 2D, 1D models, running the simulations, and then turning these results into the data to set up the data-driven or AI models. But we'll talk about it, of course, in summer. So a little bit about the case. Dhaka, some photos from Dhaka. Dhaka is a place which has a very flat topography. Like many places in the world, it has its issues, has strengths and weaknesses. One of the weaknesses is the drainage system is not very strong. It doesn't take too much, but also they suffer from monsoon periods, so they have quite large rainfall events. And if the system is not very it doesn't have large capacity to contain a lot of water, then you get obviously floods. So population there, they have to face floods every now and then. And then the objectives of the study from Farhana work was to address the risks or to assess the risks, flood risks and impacts to building structures due to floods. Farhana has also looked into the water quality issues, spatial and temporal issues, and best management practices for managing floods. This is the work, the methodology that she has applied. So she has first set up the 1D model, and then 2D model, and then coupled them, and then she ran all kinds of scenarios without impacts from climate change and also with climate change impacts and urbanization. And then she looked into some results. But then on the top of hydrodynamic flows, she had switched on the advection dispersion and sediment transport, and then she has also looked into these properties in the system. But we are not going to go this time into the water quality, sediment transport aspects. We're going to just look into the 1D, 2D. So this is where the case study area is. It's one part in the city of Bangladesh. It's called Seku Bagija. It's this rectangle that you see here, and there is also one river there. So the system, the area looks like this. There is the pipe network system with the light blue colors, and there are manholes, obviously, houses, roads, and everything. There is upstream and downstream boundary condition. There is also box culvert that the pipe network system gets connected to. And this is how the system in this particular area looks like. So it's the pipes, box culverts, and open channels. So this is how only the pipe network system looks like. This is what I call layer 1. It's a one-dimensional model. So what you see, the dark lines, the black color depicts the pipes, and then there are manholes, and the system contains pipes, but also the open channels and the box culverts. There is also a pumping station there, and the sluice gate strategy that was used to set into this model. You have the obviously pump, and there are some sluices that open up depending on the drainage level upstream and downstream from the pumping station. And then if there is a low water upstream, then the sluice would be closed, and then the pump would work. And then when the larger flows, the sluice will be open. And this was very interesting because we also looked into some real-time control strategy, but this is not the subject for this. What was very important is to look into the gully pots, the catch pits, the cesspits on the road. We often, when we set up the models, we assume these structures, these small structures, which are very important, which take the surface water from the roads, take them into the pipe network system. We often assume they are spotless, but it's not always the case. not only in Dhaka, but in many places around the world, this type of important structures, they get filled up with either debris or some litter, or sometimes they can be also covered up by the leaves, and they simply don't function. So you may have a flooding just because your catch pits are blocked off and they don't really drain the water into your pipe network system. So that's why it's important to visit the catchments and to look into the actual condition before you set up your model parameters and before you start running your models. I talked before about 1D models, and the pipe network system can be one model, one 1D model, and the other 1D model can be the road network system. And then you end up with kind of layer 2, which is the dashed lines representing the street 1D network. But then the problem with this is it runs much faster than when you employ 2D model. But then the problem is you don't get really a proper representation of what happens when the water starts spilling across the terrain. So that is then very, I would say, very rough in that estimation. That's why the 2D model is very important. In 1D model structure, you need to obviously set up the weirs to connect the below ground and above ground 1D models, and then you set up the crest weir to be on the ground level with your. And the two models would then, of course, exchange depending on the difference in head difference between the surface and pipe flows, and then the water would go either from the surface flows into the below ground or the other way around. So this is the 1D model, and that's an interesting way to think about. Sometimes you may want to choose that, but we are going to go into the 1D model. So how do we set up the 1D model in Mike Plus or Mike Urban? The history of Mike software, particularly for the urban flows, starts from System 11S, which was developed quite some time ago by Professor Abbott and his colleagues at the DHI in Denmark. So they developed one-dimensional tool, which later on split into two packages. So the one for the pipe network went on with the name of MOUSE, modeling of Suez, and the other one went ahead with the name Mike 11. So nowadays the MOUSE is very much 1D, or called Mike Urban after the changed few names. Now is all under Mike Plus, and Mike Plus contains the one-dimensional model, but also it contains two-dimensional model. So the two-dimensional model is Mike 21, two-dimensional one-layer model, which has been developed for the coastal system modeling. And then, of course, they have Mike 3D. But the two-dimensional model is really very well connected or made to applicable for the modeling flows in urban areas. So the 1D model is the setup looks like this. What you see on the left side is the network of 1D model for, in this case, we are looking the network for Dhaka, and the rectangles on the left side represent the sub-catchments. And the larger the rectangle, the larger the sub-catchment area. And then, of course, in the menu, we set up the nodes or the manholes through XYZ data, and then we set up the pipes that go from one road to another. And then if we have pumps, we set up obviously the pumps with the QH curves, weirs, orifices, valves, and so on. And then we come to the hydrological data. So then the hydrological data needs to obviously have the choice for the hydrological model. In the DHI software, that usually there are several options there. You can choose between the time area method or nonlinear reservoir kinematic wave method, or you can choose a unit hydrograph method, and there are other methods as well that you can employ. But then for the hydrological part, it's very important that you need to set up your time series, rainfall time series. And this is how the time series editor looks like in that. So what I have here, I have a couple of events, which you see here, and they are reflected in terms of the time and millimeters on the right side. So you create your time series data. Then you can also set up, depends on your hydrological model, you can set up different kinds of parameters. This is the one example. If you're dealing with the combined sewer flows, like in many places in the world, you may need to then set up also your domestic wastewater. And this is, you can see here, domestic wastewater can be also added in terms of the diurnal variation, what I showed before when I was talking about the calibration, the dry weather flow related to the domestic number of people, times the wastewater production per person per day, distributed through diurnal variation for 24 hours. You define all of that and you put it in. Then we set up the boundary condition. Obviously, rainfall drives the upstream boundary condition. The downstream boundary condition that we need to set up for the 1D model is done at the outlet points. So at the outlet of your pipe network system, you will need to set up that either fixed or variable boundary condition at the water level at the outlet. So it can be fixed value or it can vary. For example, if it is a coastal system, you may want to adjust for the tidal variation, how the time series will look like, variation at the outlet. But that's the downstream boundary condition. Here is what you can see, that the modules that you can switch on here, they can be used. There is obviously hydrodynamic module, but you can also use it for real-time control or LTS, long-term statistics. We heard before from Kaushik, who is doing his work at the National Czech University. He's running his, I understood, 1D, 2D model for long-term statistics, long-term simulations. There is also an option to do that here in the DHI software. And you can switch on the advection, dispersion, water quality aspects, sediment transport. Here, in this particular case, I've just ticked on those options, which is for hydrodynamic and rainfall runoff and for catchment discharge. I'm just illustrating how the menus look like. Of course, you have different model, will have different menus, but the data, entering the data in terms of geometry and hydrology will be pretty much the same. When you know one software, is not difficult to switch on in setting up models for different software. So moving on. So every sub-catchment needs to have a loading point, and this is what this shows. The identification is like ID here shows which manhole or which node in the system, which has X and Y coordinates, will receive the flow coming resulting from this catchment, which has percentage of imperviousness to be 65%. And then the time of concentration is maybe 8 minutes for this particular sub-catchment. Then there is a parameter reduction factor, which means which is a 30%, which means that the 70% has been lost. So this is to represent the losses. And then you have initial loss, which means that some saturation of the soil will be with the rain and not full, but you will still have some losses. This is 0.6 of a millimeter. And then there is a different time area curve and the coefficient for that type of shape. And typically the curve types are triangular or inverted triangular or rectangular shape. I mean, that depends on what model you're running. If you're running kinematic wave, you have different parameters. There is a linear reservoir, C1 type of hydrological model, linear reservoir C2, and then you have a unit hydrograph method. And then there is even more complicated hydrological model, which from memory, I think has about 16 parameters that you can need to adjust. And this is the rainfall dependent inflow infiltration, which is gets appended to your, either if you're choosing time area method, then you can add on this RDI, or if you choose, let's say, a kinematic, you can again add on. So this is a very good hydrological approximation, because it does look into all these processes that happen, and the losses and all of these very fine base flows and all these sort of different things that are important. So if that's important to you, you can choose quite complex, the hydrological calculation for your 1D model. We're still in 1D model. Then you set up your you set up your rainfall data. Then you go into your simulation period. You like in any model, you have to create your start and stop, and then you set up your, obviously it will be duration there. So in this case is 9 hours, for example, here, and then you need to set up your maybe some other parameters. But this particular model has a variable time step. So if you may fix the time step, but still the model is the computation is set like that if there are no rapid fluctuations in the computation, there is no rapid changes, the model will jump with a larger time steps, and then when the variations start to become more fine, it will reduce the time step, which is a very important for stable computations. So this is time step. As I said, you can use fixed or adaptive. So adaptive is what I just explained. And then we press button run, and then we get some results. This is the kind of report that you get, a small report, and tells you how everything went through. It gives you any warnings, errors. If you have errors, then it won't run. But warnings will let you run, but then you need to read them and to see if something is an issue for you. This is about the simulating the model. Then you go into the hydrodynamic simulation, and then you can tick on, you can choose what sort of model result, what do you want the model to report to you in terms of the results. You can get the data items for each node, for example, every link, and you can choose what you want. And then finally, when you produce your, so first you have your hydrological computation, which basically generates number of hydrographs, which is equal to the number of subcatchments. And then you feed these subcatchments as the upstream boundary condition, of course, starts from the rain and from the rainfall runoff computation. You feed through your network, and then the pipe flow computation goes. And then this is the moment when the Saint-Venant equations get solved that we talked briefly before. And then you get, as a result, something like this. So this is the 1D model result, where you can see the percentage of filling, perhaps in your pipes and your manholes, and you can color code it in a different way. And then you get this kind of maybe hydrographs, time series, and then you get a top view. Very handy, and then you can run through your simulation. So this is a 1D model. This is on the left side is the maximum water levels in the nodes. On the right side is maybe pipe discharges, and you can interrogate your results and plot what you need. Once when you are happy with your 1D model, and the model has been calibrated and produces meaningful results, and then you say, okay, I now have a model which is fit for purpose. You can plot your longitudinal plots. What you see here is the manholes. Here, in this case, we have some kind of negative slopes. What you see here, typically, if you would do the QA of your pipe network data, you would go and inspect some of these locations where the pipes go up and down, because typically pipes would be designed to go downhill rather than going uphill, downhill, and so on. So once you're happy with that, then you park your 1D model on the side, and you can go into your 2D overland flow model. So being so far in the Mike Plus environment, I will continue with the Mike Plus 2D overland flow model. In this case, we are starting with the terrain. Excuse me. I think somebody accidentally pressed the unmuted. Georgia Chaich. So yes, so we start with the spot elevations. In this case, if you come to Delft next summer, we will start this exercise from ArcGIS. So what we're going to do, we're going to start with the ASCII file, which contains XYZ data. So it's X coordinate, Y coordinates, and Z being the elevation. And what you see here is the basically a spot elevation data, which we will then process through ArcGIS and create continuous surface. We move from the vector data, point vector data, we go to the interpolate and create the raster data, because the aim from here is to pre-prepare the 2D model domain and take it into the 2D model, which will be then later on coupled. So these are the steps that you would normally do. You process your digital elevation model or digital terrain model. This is an option, of course, in the ArcGIS, that you can create hill shade, and you can observe maybe, and you look if there is any anomaly that you need to particularly look at. If everything is logical and fine, then you may proceed with your DTM or digital or DEM, whatever you choose to call it. Then you may incorporate roads, road network, and the buildings, if you like. So pinky area represents the road network, and then the small rectangles represent the buildings. And if you have your airborne laser survey data, you may filter the buildings, or you may retain the buildings, and you can create. I'll show you later how the animation from Mic Plus can be. You can use even the building heights. So this is again the DTM processed. Now, when we are fully satisfied, maybe sometimes you may create a different versions of your DTM. Maybe it can be one just incorporating the roads, so the bare earth with the roads incorporated. Let's say the curbs 20 centimeters high, so you can embed that into your terrain data. And then maybe another one you can create with the buildings. If you come again to Delft, we'll do both. You will practice to do that both. And then after that, you are ready to export that into the ASCII file. And then from there, which is a text file, and then you go into the Mic Plus 2D. Since this two-dimensional model comes from the coastal area, you will get bathymetry here, which is obviously in this case the terrain data. You can either approximate either have it through rectangular grids or flexible mesh, and then you will set up your 2D model, and then later you will also bring in your 1D model, but we'll talk about that in a moment for the coupling. So the coupling can be done at the manhole level, outlet, and so on. And then when you couple it, your 2D model, raster representation with your 1D model may look like this. A few more parameters we need to set in our 2D model before we can start simulations. Obviously, what makes a difference is what sort of values of your surface reference you can put. Here I have an example of a 32 Manning's M value, or you can go with Manning's N, which is 1 upon M. But here is Manning's M, and what this means is that I have set the value of 32 throughout the entire model domain, 2D model domain. So every cell has this particular roughness value. But if you want, you can vary. You can create different varying domain. So this is uniform, but otherwise you can have varying roughness values within your 2D model domain. The next parameter you need to set up is the 2D eddy viscosity, and this parameter influences the propagation of turbulences in the water based on the velocity of flux. And this parameter can be used to improve the model stability very much, because you may get instabilities and your model may crash, and then you can play with the different values of the eddy viscosity. Okay, the initial conditions. This is very important for the 2D model. In terms of wetting and drying and this kind of things, you need to set up initial water level. So there must be, you cannot start completely dry. So you need to start with some water level numerically. So typically it goes very, very low value, but still to handle this wetting and drying problem. Then you start coupling 1D and 2D models. Then you get your, like what I have here, I have a runoff, I have a network, and I have a 1D, 2D, and then you can, on top of that, if you want, you can even go into your advection dispersion and things like that, but not in this particular simulation. Then you set all your layers that you want for coupling. Then you go into your simulations, you press the button run, and then you get at the end something like this. So this is your 1D model, 2D model result. The blue represents the water depths computed, and the darker the color, the more deeper the water. And you can navigate throughout the entire simulation period. So the green vertical line represents where you are in the particular point in time through your simulation period. And then you can see how the peaks represent the highest computed water level in your simulation. And then finally, so when you set up your 2D model, starting from GIS, bathymetry, DTM, we talked about the 1D model, you couple the two together, you run. You can also create from this 1D, 2D computational framework, you can create a 3D visualization. And this is typically done in Mike software through Mike Animator Plus, which is a quite straightforward software to use. Once when you generate your result file, you bring it into this environment, and it's a very straightforward to create something that maybe is your stakeholders, maybe for your communication with stakeholders might be useful because people can relate in 3D where the flood goes. And this is an example from the Mike Animator where you can see 1D, 2D model. So the flood propagates through urban area and goes around the buildings and creates. And then you can also zoom even further, and then you have a bit more zoomed locations, and then you can try to relate how this works. This is, of course, powerful to do with buildings, but then when it comes to the depth damage assessments, then your buildings can represent a challenge to compute these depth damages. Then in that case, maybe you want to remove the buildings, because then the water that gets on the top of the footprint of the building, the depth will be used to calculate the depth damage values. So then you may get some results like this, and that's pretty much where I'm going to stop with this discussion on the Dhaka case. Of course, we did here the water modeling and so on. I think we are going for another probably 10 minutes, I would say. I will show you. So this was a Dhaka case. Of course, we can discuss that further, but I will show you very briefly one more case which follows a similar pattern of model setup and everything. This is for the case in Thailand, where we worked straight after the 2011 Thailand floods. So what you see on screen is the location of the study area. This is Ayutthaya, which is about 2 hours on the north from Bangkok, and this area contains 3 rivers, and it's they call it Ayutthaya Island. So there's a urban area within, but it's also very, very unique area because it's a really culturally, religiously, spiritually for Thai people. It's a very important area. It contains it's also UNESCO heritage site. It contains very interesting objects. It used to be a capital of Siam in 15th, 16th century, and then later moved into Bangkok. But this area is a highly touristic, very attractive, and also very important for Thai people. And in 2011, it was severely flooded. So we did some work there. There were 5 storms that occurred in that period in 2011. And this is how that area looked like in Thailand. And the water remained on the ground for the period of 3 months. In some places, it remained with a depth of 2-3 meters for all that period. It was really a significant damage and impact on the population and everything. So this is what I'm talking about, is UNESCO heritage area. So the area is normally dry, but here you can see how the flood waters have come very close to these monuments and the objects. So we did a study there where we looked into the flood risks. So we built the 1D, 2D models for the hazard assessment, vulnerability. We did quite detailed work together with UNESCO Bangkok and also with ICOMOS people, and we had 33 different stakeholder groups. And we really, what I'm trying to say here is that it's quite complex study. but the models that we've set up and then how we turn the results into some visualization means, which I will show in a minute, was very, very effective in talkings with the stakeholders and to sort of communicate with them and to get their feedback. I'm not going to go into this, but this is what's interesting for this lecture today is that we are on the left side, we see the entire network of Chapraya River. And because it's a quite a large net, we have it, we did use it 1D model, in this case, Mike 11, for the entire network. But then we kind of did the nesting. We did the, what you see, the shaded area on the left side has been used further with a higher level of details. This is a model number 2. So we use the boundary condition from the first model. And then we extracted, put into model 2. And then the next shaded area on the model 2 is actually the 2D domain model. This is Ayutthaya. So what you see here is that basically is going from one 1D model to another 1D model and going to 1D 2D, which is the situation 3. And I'll quickly show you how this looked like. We ran different options. This is 1D and 2D, and I'll quickly just run the one. Just a moment. Training. Yes, it's in here. Just 1 second. Yeah, this one. Let me open up with the right file. Reference. Open with. Doesn't want to. If I try to open like this, it will not work, I think. I just want to show you. No, it won't work. But I need another. Open with, yeah, this one, sorry. Yeah, this one, I was opening the wrong things. Okay, what I want to show here is that for our model analysis, we did set up this is 1D, 2D model results. In the upper left corner, you see the scenario do nothing. And then as we move on through the other sequences, we see partial flood protection done in the second graph, and then more flood protection, more, and so on. And then you can see how that looks like. You can see how the water comes from the rivers along the. This is simulating 2011 flood event that took place, flooded 2/3 of the entire Thailand. So what you see here, how flood rate propagates in the 2D model. We also cross-calibrated all of this with some satellite images. And then you can see how the effectiveness of certain infrastructure works are working. You can see here on the upper left corner, nothing done, then some portion of work was done. And the very, very last thing I want to show, because I think we are finishing in 5 minutes. So this is from Ayutthaya case. This is a second case. First, I show the Dhaka case, and it's the sequence of work is pretty much the same. What is interesting to show is that we have taken the model results, 2D model results, and put them into the animation. And this is the animation that I think it's a wrong player. I need to do this open with and pick the same, yes. So this is another, oops, we don't need a sound. What you see here, it's another MSc work of one of my students from Thailand. What she did, she has taken the model results, 2D model results, into the landscape architecture rendering software, which kind of speaks more than just looking at the Mike Animator or 2D flood maps in GIS. So what you see here is she has kind of developed and you see now here the model results and also looking at the effectiveness of some measures. So for example, here you see on the left side, on a dry day, how implementation of new measures would look like. On the right side, you see how, and this is again taken from the model results and put into a different form of communicating the model results, 2D model results to the stakeholders, and comparing different scenarios and effectiveness and how this is again another comparison, how it will look like. So So what I'm trying to say here is that the 2D models are good. They'll produce nice results in a 2D visualization framework in GIS maps, but maybe not always very easily for everyone to understand, particularly if you don't have technical background. But then moving to maybe some 3D animations, and particularly using this kind of software to turn your 2D model results into the landscape architecture software may be even more useful. And this is what we found in Thailand to work very well to communicate 2D model results to the stakeholders. And having said that, I think I will wrap up. So what we've done today, we looked into the 1D models, 2D models. We looked into the data that's needed to set up both 1D and 2D. I've shown you briefly the typical menus and the data that's the data setup that's needed for one of the softwares. And of course, this is a very short course. We cannot cover all the more software than just one. I've picked the Mic Plus, which is a DHI product, very good software, very stable, although it's a commercial and then it costs the money. But nevertheless, when you know one of them, then it's not difficult to use and to know the other. So that's about it. And I will give it to Zoran to take some questions. Sorry for my throat.
Thank you, Zoran, very much for a very interesting lecture. And you have been talking for a few hours already, so don't worry.
Yes.
Take some water, something. Yes, let's go straight into the Q&A session, and then we can wrap up the whole training day. Do we have any questions for Zoran? As before, if you want to ask a question, just let us know, first of all, or just switch on your microphone and ask the question. But do say what is your affiliation, please. Okay. Whilst you're thinking about this, maybe I can ask a question. And it's related, Zoran, to this last part, the visualization. I know that quite a bit of work has been done about this, and it is a very important part of conveying the message about the floods and so on. So what do you find so far to work the best? These kind of animations that you showed us toward the end?
Yeah, it depends.
Some people are doing augmented reality. They are literally taking a video of the area and then just putting artificially the water level, how far the water might stretch.
Yes.
Just what is your experience with this? What works best and what is currently available?
Well, it's a very good question. It depends who are you dealing with. If you're dealing with the technical audience, maybe people who have a water background, water engineers, then navigating through some GIS maps and showing some discharge hydrographs and things that can be sufficient and very well effective. However, if you work with a larger and diverse group of stakeholders, like we did in this project, we had 33 community groups, and then we had also the people from UNESCO and the Ministry for Culture and so on. So we really found that this kind of turning all the 2D model results into this kind of representations that I just shown was quite effective. And people could relate, they were impressed with the work, and they could provide more, I would say, structured feedback in what they like, what they dislike, how they would, they could perceive better what the future may look like with a particular measure or another measure. So it worked quite well for us for that purpose. But again, depends who you're dealing with.
Yeah, I agree with you. Yeah, but we are certainly going to see some development there, I believe, especially with the AI and all these computer vision techniques and so on. It's going to become even more realistic. You would kind of have to use less of your own imagination and just see almost one-on-one what would happen.
Yes, I may show you also. We had some. Okay, maybe I'm not going to search for slides now. We had the. I know that Natasha is not here, unfortunately, but she could tell you a lot about the. They have it. It's called a flood room. So what they have is actually physical building kind of a room which has a house belongings like chairs and seats and whatever couches and TVs and things like that. So what they have done when they were dealing with their stakeholders, they would pump the water literally inside, and the people who are part of the decision making but not necessarily living on the floodplain, for them is good to experience to see how it is to live with the areas which flood often. And then they ran the exercise of moving the furniture. They gave them a time, so they would pump the water in and moving furniture from one point to another, so they would really experience that. But nowadays, the technology, as you said, is very much moving towards augmented and the virtual reality. And like augmented reality is really taking a lot. Now, even you go buy in a shop a piece of furniture, they use the augmented reality apps that you can capture your living room and the chair that you want to buy, and then you can. So that is also happening with these goggles and everything else people are doing nowadays. But I have not seen personally much of that. I have very much stopped at the level of my last study where we did was with this kind of landscape architecture, animations, and things like that.
Yeah,
which worked quite well for us.
Yeah, indeed. Any questions for Zoran? Don't be shy.
Can I ask you something?
Yes, please go on.
First of all, thank you for your lecture. And today you showed us mic software, and I know there are different softwares for flood modeling. So do you have a chance to use, for example, TwoFlow or some other softwares? And do you have any recommendation on which one is better if I want to use these results for training a machine learning model?
I wouldn't go into saying explicitly, well, this is much better than the other. I think all this software is good for different purpose, and as long as you know how to use it and what are the limitations, you can get fantastic work out. If you don't know to use even the best, the most the software with the most functionalities, you will still have a problem. So I think to get the reliable and proper results really rests on the shoulders of the modeler rather than on the modeling system. So the modeler needs to really understand what he or she is doing, the limitations, and to how to interpret the results, and not to force the parameters of a particular model. If you're calibrating something, you should not force the parameters to fit with the curve, but you should stay within the boundaries of a physical values, realistic physical values, like a reference coefficient. You should not twist these values to go to some unrealistic values just because you want to fit the curve. So that's an example. So the modeler really needs to be able to understand the results, to see what's happening, and then of course, if you have a model which, if you compare 1D versus 2D model for flood modeling in urban areas, obviously a 2D model will be much more robust and much more reliable because of the physics. But other than that, in terms of the software packages, I would not say this is better than that, because they're all good. They have advantages, disadvantages. One of them maybe is a regular structured grid, the other one is a flexible mesh. Somebody may tell you, well, this is not good because you cannot capture the edges in urban areas with rectangular grids. So you should better go with a triangular shapes and things like that. That's another aspect to consider. But again, it's all in the hands of the modeler.
Yes, thank you, Zoran. Maybe I can follow up on Yasmina's question. When we do the machine learning, we need to collect a lot of data by running these models many times. And running them, we would like to do this in an automated way. And you can always, do this through the input-output files, but it's nicer if you can link directly through software code. According to your best knowledge, which of these models we know that Swim is quite good with this because it's freely available, quite open, and so on. Not entirely open, but reasonably open to automate. But from the commercial software, how many of these do have those kind of functionality built into them that you can do a batch run of a number of simulations in an automated way without having to write some code yourself?
Well, I think you can. Well, for some of them, obviously, you need to run some a small piece of code to set up the to write your input file and generate the result file, and then sort of that's, of course, it's not difficult to do. It's straightforward. Some other software, they may have more of these functionalities built by the software producers, but generally speaking, I think that's not a really challenge anymore. I mean, people do that batch runs and no problem. You mentioned Swim. Swim is a great package. It's a very easy to use. It's straightforward. You said it's open source. I've used it with my students many times. We have coupled our 2D model with the Swim. It works very well. Of course, there is one drawback that some people who are dealing with the computational modeling would tell you that okay, maybe implicit versus explicit scheme, and then Swim uses explicit scheme, which means it's more sensitive to a current number. Should not be
less stable numerically.
So you have to reduce their time steps and things like that. You need to be careful, particularly if you have a more complex network and you have maybe some ancillaries and you have some pumping stations and overflows, and then some instabilities can propagate and then it can cause a problem. Whereas software with implicit scheme can run stable with higher current numbers, and so that's numerically comparing one. But then explicit is much easier to code, and to create implicit is much more challenging to code. I mean, at the software production. Yeah,
it is indeed. Yeah, these are the trade-offs. Okay, any further questions for Zoran from anyone?
If I may just say something, if nobody reacts, is that I can see that we have a bit more time because Natasha's slot was planned. But if you want, let me see, we have another maybe 15-20 minutes. I can show maybe one more case. Or we stop here. I'm happy to do both.
Yeah, I'm happy to do either. It depends really on the people what they want to do.
Maybe.
Well, if there are no further questions, maybe you can do another 10 minutes of presentation. Show us one more case, and then we can wrap up the training. Yeah?
Exactly. Yes. Because I know that Natasha would have given some interesting presentation by now.
Yeah.
Okay. What I'm going to now jump into. We're gonna now fly over to the Caribbean region from Asia. Let me see what's happening here. Okay. Yes, we're gonna go to Saint Martin. So Saint Martin is the island which is located in the Caribbean Sea. It's the island that shares administration between the Dutch side and the French side. What we're seeing now on the screen is the view towards the Dutch side. It's a beautiful island, has beautiful, pristine beaches and everything else. But of course, being in the tropics, it suffers from tropical storms and hurricanes and things like that. So I want to show you how 1D, 2D models can be set for flood purposes on the land, but also you can add the coastal component. So here we have added also the coastal component, and we have run the simulations with the hurricanes for the purpose of flood risk assessment.
Zoran, sorry to interrupt. Maybe just go to the display settings.
Yeah.
So we can see a larger main
I know. That often happens. Let me see. Yes, sorry that I overlooked that.
No, that's good.
Yes. Okay.
Yeah, good.
It's better now. Okay, great. So we are moving through there. So this is Saint Martin on a nice, beautiful day. Everything beautiful, really. But then you get some rainfall events. Tropical storms typically happen out of blue, and then you get and of course you have hurricanes, which is a totally different story with the high winds and sometimes followed with a heavy rainfalls can cause devastating damage. But this, what you see on the screen, is not a hurricane impact. This is just a rainfall event which took place for a period of maybe 1 hour. Flash floods, which have brought a lot of damages and also, unfortunately, some human losses. That was in 2005, and this is where the island government has asked, back then, UNESCO actually, to help, and I went there and with my team, we together did some work. So this is the talking a little bit about how did we go about modeling. So what you see here is the terrain data. Obviously, the kind of bluish color represents the hills, and the topography of the island is quite hilly. So you get this flash flood type of effects. But the island also has some kind of streams, water courses, not really massive rivers, but the water courses. And then obviously they have some drainage problems. So how did we go about model setup for this? We have delineated the entire island into the catchments and sub-catchments. And I mentioned before there is a transboundary aspect here as well, because the northern part is French territory, southern part is the Dutch territory. So we worked well with both governments and we to produce some flood maps, but I'll focus now on the Dutch side. So this is the red line depicts the borderline between the two areas. So this is a Dutch side. So you see, we ran very nicely and very easily this function that I explained before in GIS to delineate subcatchments, which of course can be challenging in the flat terrains. And then what you see, the light blue color depicts the channels, open channels, and also there are some smaller sections with the pipes there. So these open channels are modeled with Mike 11 back then. So what was interesting to also think about by when doing these type of studies, applying 1D, 2D models, is to develop scenarios for the existing development situation and also for the future development. So the existing development in the sense of the percentage of imperviousness that's currently present on the island, and you get it very well from the satellite images, and then you can define the degree of what's pervious, impervious. And then for future development, we went to the government, we discussed about their future planning, and then they gave us their ambitions. And then what you see below is the future development scenario, which has the darker colors, which means more impervious areas. What you see the dark color on both, on the left side is is one area which is the runway of the airport. So we have worked with the we had a 10-meter DTM, by the way, that was done quite some time ago to start with the terrain, but then we also went into the sea to extend the model, and then to run for the hurricane simulations. So what is also interesting there, we had a challenge. There was a need to set up these models as soon as possible because the island government wanted to look into some kind of no-brainer measures. So we didn't have time to do some measurements for a long time. So we went with a kind of model, not calibration, but rather validation. So what you see here is the photo of the principal of one primary school, which shows that how far was the flood water that happened on a particular date, which we would simulate through our 1D, 2D models. So we've used then to calibrate the depths of a 2D model against these eyewitness records. And then what you see here is the dead point on the terrain in our model was showing that this is 0.73 of a meter, which is kind of approximating after calibration and playing with some roughness values. We came up to kind of agreement with this model validation. And then we went around the households, talking to the people who showed us actually the marks, the watermarks. And then we've used that to calibrate 2D model, because it's really challenging to calibrate a 2D model, because, you know, in the all closed channels or open channels, you can put the different instruments and do that, but the 2D model is always a challenge. So we've used the eyewitness records as the source of information to calibrate the 2D model, and so on and so on. So then we have simulated different aspects of the channels and the pipes, and then we try to explain them in terms of the capacities. And what you see, red has a capacity of 1 in 5 year event. Then other color, yellow, brown, shows 1 in 10 year event. Green shows the capacity of a particular section, 1 in 20 year, and so on and so on. I'm not going to go into these details. We've then looked into the vulnerability. We ran the 1D, 2D models. And then we went into the into the evaluation of the effectiveness of these models from 1D to the simulations. On the left side, what you see is the 1 in 100. I think it was 1 in 100 year event. Coincidentally, it happened to be 100 millimeter an hour intensity. On the left side, you see no infrastructure improvements or particular infrastructure improvements that we discussed with the government would be implemented. So do nothing scenarios on the left side. You see the hazards comprised of the depths and velocities. And you see the color coding goes from yellow to red being the extreme hazard and yellow being the low hazard. And then you see the effects on the right side, how a particular retention basin in that particular area would alleviate the flood risk. And then you see how the pattern of the hazards reduces. So this was a very interesting way to communicate the results. And then we would go through this is 1 in 50 year event. You see the effects of that particular pond that we proposed to be constructed. Then you see how it eliminates completely the extreme hazard. So the red color disappears. And then this is a 1 in 20 year event, then 1 in 10 year event, and you have 1 in 5 year event. So this is also, I want to show here how the 2D model results can be used effectively to discuss with some stakeholders. Of course, that fancy animations that were produced in Thailand were not produced here, but this was already good enough for the purpose that we had to show the effectiveness of different measures, which was used as a basis for the government to improve the situation on the island. But then we go further, and I want to show you now one more part, and I'm done. And it is that how we went with the bathymetry. So we have set up. This is an interesting thing, maybe to say. We worked on the bathymetry data together with people from NASA. So I personally had access to their EO1 satellite to every night before the satellite would pass tomorrow, in particular time, I would look into the weather forecast and decide whether I'm going to use the satellite images. And this is high resolution satellite image EO1 to get the different values for the waters, actually for the bathymetry. And then we have used the jet ski measurements to measure the actual depths and then cross-correlate these two. And then for this purpose, we've used the support vector machine to digitize the bathymetry, which we then brought into 2D model and used it as a basis to simulate hurricanes. And for the deep waters, we've used from a Dutch Royal Navy some data to complete the data set. This is how the nearshore data collection. This is on the right side, the EO1 image, satellite EO1 Earth observing 1. And then on the left side, you see how we created eco sounder. And then by running through the region, we collected measurements. So what you see here, for example, yellow areas are the measure data performed with the eco sounder. And then after that, we did interpolation around through the support vector machine, by the way, to create and this is how this jet ski looked like. And this is how the echo sounder works. It gets the depth. And then these are the paths where we went around the island, somewhere in some beaches, in some areas where the government told us it's more important because of the airport and the water infrastructure and so on. We did more narrow spacing and then maybe more course in the other parts. With this, we produced I'm not going to go into all this, how we process the data, but we came to the point of using the support vector machine, yes, this one, to interpolate the data. And it worked quite well. We got nice smooth area and we built it into the coastal model. And I'm going to show quickly how that looked like in a simulation for the Irma. Yeah, this one here. Oops. Off the width. Yes. So now is the 2D model running the simulation. In the upper part, you see the wind effects, and then you see the storm surge pulling up, and then you see how it approaches next to the island of St. Martin, which we have then used that as a boundary condition for our more detailed model around the island, which contained also 1D network, 2D terrain. But this is too coarse. We could not use, of course, couple this with 1D and all that. But we used it as a boundary condition for the other model to simulate the effects of how the storm surge can affect the island in combination if there is a rainfall-induced flooding on the island as well. So this is an example how also the 2D models can be used for coastal applications. And we have also extended this application into the sewage, and I'm finishing here. For the sewage measurements, because they have two outlets here which are causing some pollution problems in this bay. So the island government asked us, what do we do with the sewage? Can we continue discharging? There was because they also have a wastewater treatment plant, but during extreme events like hurricanes, they would dump the sewage during emergencies into this bay. They asked us to look into if we would extend and do the deep sea outfalls. And this is what you see, the possibilities for the deep sea outflows, how the effects would look like there. So then we did these simulations, and I show you the results. This is, for example, simulation from that model. Yes, this is the 2D model simulation with the effects of advection dispersion, and how if they would dump this is the channel which would take the sewage right into this bay. We also here modeling the surface runoff and everything together, but then with the advection dispersion, and then you see how because of the configuration of the bay, you see how the pollution stays within the bay. And then they asked us to model another scenario, which is this, to extend the outlet into the sea further, because obviously with the salinity, temperature, and these effects, the sewers would the concentration of pollutants would be processed with the nature. Then we came up with the optimal configuration. So what's here showing that if they would extend the outlet to be at this point, also not good because of the bay, the water the pollution would still sit here for a few days. So if they would want to do that, they would need to really extend it for a couple of more kilometers deep in the waters. But then we've modeled everything in terms of the hydrodynamics, but also water quality and advection dispersion. So this is a combination of looking into the floods, but also looking into the pollution aspects, combining with some coastal models to extend the scope of work. So this I just want to show an additional possibility with 2D models when you deal with the coastal areas.
Okay, thank you very much, Zoran. Again, interesting stuff. We have a few minutes left for a burning question. Does anyone have a question for Zoran related to the last part or anything beforehand you've heard? No. Well, if not, maybe we should wrap up this event. It's been a few hours already. It's not easy on you, Zoran, but it's not easy on the listeners either. Yes, thank you very much for doing a great job in doing all these presentations, and you're certainly doing some impressive work. And like you said, there is a lot more of this if you come to the summer school.
I was just about to say that.
So
Hope to see you all in Delft in July.
Yeah. So over to you, Veljko, to wrap up the whole event. Yes.
Thanks, Zoran, and thanks, Zoran Vojinovic, for this amazing talk today. You did a tremendous job. And thank you so much. Yeah, I mean, I just wanted to advertise summer school again. And wanted to remind everyone, so we're going to have another expert training before the summer school, probably sometime in April, March or April. You'll get more info on that when we fix the date. But yeah, stay tuned with all the artifact things on the artifact-project.com website. We'll have all the updates there with the news and activities that are ongoing. And yeah, I just want to invite young researchers to our summer school. There's going to be special activities for young researchers. We had hackathon this year, and we'll have more activities for the summer school. So it's not just a learning opportunity, it's also networking and social event. And we are hoping you'll have a good time coming to Delft. But yeah, that was what I wanted to say. And again, thanks to Zoran Kapelan and Zoran Vojinovic for this session. It will be online in the next day or two. We'll put it on YouTube, and you can share this presentation with everyone who couldn't make it today. And yeah, if you have any questions, you can reach us through the email, through the website, or through our personal emails. You know the drill. You're in research. If you hear you're a researcher to us. So you know how it works. Thank you everyone again, and enjoy the rest of your day and the weekend. Bye.
Thank you. Bye-bye, everyone. Bye.